Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, ideas move at an unhurried pace, and the universe is explored softly enough that you can simply listen, relax, and let the mind wander while the body settles in for rest. Tonight's journey drifts toward a place that has hovered above every human who has ever lived, a pale companion that has watched the oceans breathe and the continents shift, a world so close that you can cover it with your thumb, and yet so distant that reaching it remains one of the most difficult things our species has ever done. This evening, we're going to explore a quiet and curious question. If humans walked on the moon more than half a century ago, why does returning there seem so difficult now? At first glance, it feels almost backwards. Technology is more advanced than ever, computers are billions of times more powerful, materials are stronger, lighter, and smarter. We carry devices in our pockets that can calculate trajectories faster than entire rooms of machines once could. And yet, sending people back to the moon has taken decades of planning, redesigning, and careful preparation. It's a bit like discovering that rebuilding an old wooden ship is harder than building it the first time, even though you now have better tools. Time changes things in ways that aren't always obvious. Skills fade, priorities shift, entire ways of doing things quietly disappear, and sometimes the very progress that makes new journeys possible also introduces new challenges that never existed before. But before we ease into that story, let me ask you something simple, something gentle to anchor you in this moment. Where are you listening from tonight? Is it late evening, the world outside already quiet, or early morning, with the day still unfolding? Perhaps there's a soft glow from a lamp nearby, or the faint hum of distant traffic, or maybe only silence and the slow rhythm of your own breathing. Whatever time it is, wherever you are, I'm glad you're here. And if you find this journey soothing, or interesting, or simply a pleasant way to wind down, I'd be quietly grateful if you gave the video a like and perhaps subscribed. It helps this calm little corner of science reach others who might need a peaceful pause as much as you do. Now, settle in, allow your thoughts to slow just a little, and let's begin to drift toward the moon. For most of human history, the moon was not a destination. It was a presence. People watched it rise and set, noticed its phases, and used its steady cycle to mark time. Farmers planted by it. Sailors navigated by it. Poets, philosophers, and children lying in the grass all wondered about it. Yet no one, for thousands upon thousands of years, seriously believed that human beings would ever stand on its surface. Even in the early 20th century, the idea of travelling to the moon still belonged mostly to dreamers and science fiction writers. Rockets existed, but they were crude, unreliable, and limited. The energy required to escape Earth's gravity alone was enormous, and the challenges multiplied with every kilometre gained. Air grows thin, temperatures swing wildly, and the protective blanket of the atmosphere fades into nothing. Space is not empty in the comforting sense. It is empty in the way a desert is empty, vast and indifferent, offering no help at all. And yet, within a few decades, something remarkable happened. Humanity did not just imagine reaching the moon. It did it. Machines were built that roared with controlled fire, climbed beyond the sky, and carried people farther than anyone had ever gone. For a brief period in history, travelling to the moon went from being impossible to being routine, in the sense that it was achieved more than once by different crews, with a growing confidence that the process could be repeated. That period feels, in hindsight, almost like a dream. Grainy footage of astronauts bounding across grey plains, a flag standing still in the airless silence, a boot print pressed into dust that has remained undisturbed for decades, exactly as it was left. And here is where the quiet mystery begins to take shape, because after those journeys ended, something unexpected happened. Humanity stopped going, not because the moon vanished, or because it became less interesting, or because we suddenly decided it was no longer worth visiting. The reasons were more subtle and more complicated. They had to do with money, with politics, with shifting priorities, and with the simple fact that maintaining the ability to travel to another world is not like maintaining a road or a bridge. It requires a living, breathing ecosystem of knowledge, skill, industry, and experience. And when that ecosystem fades, rebuilding it is not as simple as flipping a switch. Imagine a master watchmaker who spends decades perfecting an intricate mechanical clock. Every gear fits perfectly, every spring is tuned, the clock runs beautifully. But then, over time, the workshop closes, the tools are scattered, the apprentices move on, the notebooks are misplaced. 50 years later, someone decides to build the same clock again. They have better metal, better lighting, better measuring instruments, and yet they discover that something intangible is missing. The quiet familiarity of hands that knew exactly how tightly to turn each screw. The memory of tiny adjustments learned only through years of experience. Spaceflight, especially human spaceflight beyond Earth orbit, is like that clock. It is not just technology, it is practice. It is thousands of people who know exactly what to do, often in ways that are difficult to write down or fully capture. There is also another layer to this story, one that often goes unnoticed. The world itself has changed since the first journeys to the moon. The standards we hold for safety are different. The expectations of the public are different. The political landscape is different. In some ways, we are more capable than ever. In others, we are more cautious, more deliberate, more aware of risks that were once accepted with a kind of quiet resolve. And caution, while wise, has a way of slowing things down. Consider for a moment what it actually means to send a human being to the moon. A rocket must lift off carrying hundreds of tons of fuel, because escaping Earth's gravity requires extraordinary energy. Every component must work perfectly, because there is no roadside assistance in space. Guidance systems must calculate trajectories with exquisite precision, because missing the moon by even a small margin means drifting endlessly through the void. Life support systems must provide air, water, and temperature control in an environment that offers none of those things naturally. And then, once there, a spacecraft must descend onto a surface that is covered in fine abrasive dust, with gravity only 1/6 that of Earth, under a sky that never turns blue. Landing is delicate. Taking off again is delicate. Returning safely across hundreds of thousands of kilometers is delicate. It is, in other words, one of the most complex undertakings humanity has ever attempted. What makes the story even more fascinating is that the first time this was done, it happened under circumstances that were very different from today. There was urgency then, a sense of competition and national pride that drove enormous resources into the effort. Entire industries were reshaped almost overnight. Engineers worked at a pace that would be difficult to imagine now. The goal was clear, the timeline was short, and the willingness to accept risk was much higher than it would be today. That doesn't mean the people involved were careless. Far from it. They were brilliant, meticulous, and deeply committed to safety. But the world around them was different. The tolerance for uncertainty was different, and the scale of investment was, in many ways, unprecedented. Today, returning to the moon is not driven by the same forces. The motivations are more varied. Science plays a larger role. International cooperation is more important. Long-term sustainability, building habitats, and learning how to live beyond Earth are part of the vision. These are ambitious goals, but they also make the journey more complex. It is a bit like the difference between sprinting to a mountaintop and planning to build a small village there. The first requires speed and determination. The second requires patience, infrastructure, and a deep understanding of the environment. While all of this unfolds, the moon itself continues exactly as it always has, orbiting Earth in quiet indifference. It rises and sets, it waxes and wanes, it lights the night for travellers and insomniacs and anyone who happens to look up and notice it hanging there, serene and distant. There is something strangely comforting about that. The moon does not hurry, it does not demand, it simply waits. And perhaps that is why the question of returning there feels so intriguing. Not because the moon has changed, but because we have. Our technologies, our societies, our priorities, even our understanding of what it means to explore have all evolved. The journey back is not just a repetition of what was done before, it is in many ways an entirely new kind of undertaking. Long before the moon became a destination again in plans and proposals, there was a single night when it first became a place where human footprints existed at all. To understand why returning there today is such a careful and complicated process, it helps to linger for a while in that moment, because the first time humanity stepped onto another world did not feel ordinary even as it was happening. It felt improbable, fragile, and strangely quiet. It was July 20th, 1969. On Earth, the day unfolded differently depending on where you lived. In some places it was evening, in others deep night, and in still others early morning. Families gathered around televisions, many of them black and white sets with small screens and flickering images. Signals travelled across continents and oceans, bouncing from antennas and satellites, carrying pictures that were grainy and indistinct, yet unmistakable. What people were watching was not just a broadcast. It was the first time in history that human beings were about to step onto the surface of another celestial body. The spacecraft carrying those astronauts had begun its journey days earlier, rising from Florida on a column of flame and thunder so powerful that the ground itself seemed to tremble. That launch alone was an event that drew enormous crowds. But the true weight of the mission was felt more deeply in the quiet hours that followed, when the rocket was gone from sight and the spacecraft was only a distant signal moving through space. Travelling to the moon is not quick. Even at the speeds achieved by the spacecraft of that era, the journey took several days. Inside the command module, 3 astronauts moved carefully in the confined space, checking systems, adjusting trajectories, and performing routines that had been practiced countless times on Earth. Outside there was nothing but darkness, and the steady curve of the planet slowly shrinking behind them. One of the most striking things about spaceflight is how calm it appears from the inside, at least much of the time. The violence of launch gives way to long periods of quiet. Instruments hum softly. Fans circulate air. The sensation of weight disappears, replaced by the gentle drifting of objects that are no longer pulled downward. The extraordinary becomes, for a while, almost routine. As the spacecraft approached the moon, the next phase of the mission began. 2 of the astronauts transferred into a separate vehicle, the Lunar module, a machine designed specifically to descend to the surface. It looked fragile, almost insect-like, with thin legs and wide feet meant to absorb the impact of landing. Unlike the sleek rocket seen in science fiction, it was not built for beauty. Every surface, every angle, every component was shaped by the demands of weight, fuel efficiency, and the realities of operating in vacuum. Descending to the moon is a delicate operation. There is no atmosphere to slow a spacecraft with parachutes. There is no room for large errors. Engines must fire with precision, reducing speed gradually until the craft hovers and then settles onto the surface. Too fast, and the landing would be catastrophic. Too slow, and fuel would run out before touchdown. As the lunar module approached its landing site, something unexpected happened. The onboard computer began displaying alarms, signals that indicated it was receiving more data than it could process comfortably. For a few tense moments, the situation was uncertain. Engineers on Earth examined the telemetry, working quickly to determine whether it was safe to continue. The decision came: proceed. Those minutes, though brief, carried an intensity that was felt by everyone involved. Inside the spacecraft, the astronauts remained focused, scanning instruments, communicating calmly, adjusting their descent. Outside, the surface of the moon drew closer, a landscape of grey dust, scattered rocks, and long shadows stretching across silent plains. Finally, the engine shut down. The lunar module rested on the surface, a message was transmitted back to Earth, simple and direct, confirming that the landing had succeeded. Yet even then, there was a pause. Preparations had to be completed before anyone could step outside. Equipment needed to be checked, suits pressurized, procedures followed exactly. Hours passed while the world waited. Waiting in moments like that feels different. Minutes seem longer, attention sharper. People leaned closer to screens, listening to static-filled voices, watching images that flickered and faded, knowing that something unprecedented was about to happen. At last, the hatch opened. The first astronaut began to descend the ladder, moving carefully in the bulky suit, each step deliberate. A camera mounted on the spacecraft transmitted the view, showing boots moving down metal rungs, then pausing just above the surface. And then, gently, a foot pressed into the lunar soil. The words spoken at that moment have been repeated so many times that they feel almost familiar now, yet at the time they carried a weight that was difficult to fully grasp. A human being was standing on another world, speaking calmly, describing the surface, testing the ground beneath his feet. What made that moment remarkable was not only the achievement itself, but the stillness of it. There was no wind, no sound, except the voices transmitted by radio. The sky above was black even though the sun shone brightly. The horizon seemed closer than expected, curved more sharply than on Earth. And beneath each step, the dust compressed into prints that would remain unchanged for centuries, perhaps longer. Back on Earth, people reacted in many ways. Some cheered, some sat in silence, some felt a sense of pride, others a sense of wonder, and many simply felt quiet amazement that such a thing was possible at all. It is easy, looking back, to think of that night as inevitable, as the natural result of progress. But at the time it felt anything but inevitable. The challenges had been enormous, the risks real, and the outcome uncertain until the very last moments. After the first astronaut stepped onto the surface, the second followed. Together they moved about the landing site, conducting experiments, collecting samples and taking photographs. Their movements were slow and careful, influenced by the reduced gravity and the stiffness of their suits. Each step sent small arcs of dust drifting outward, falling gently back to the ground. Time on the surface was limited. Every activity had been planned in advance, every minute accounted for. The environment offered no forgiveness for delays or mistakes. Life support systems had finite capacity. The ascent engine that would carry them back to orbit had to function perfectly when the time came, and so, after only a few hours, preparations began for departure. Leaving the Moon is, in some ways, even more demanding than landing. The ascent stage of the lunar module had to ignite and lift off from the surface, leaving the lower portion behind. There would be no second chance if the engine failed. No rescue mission could arrive in time. When the engine fired, it worked as designed, lifting the small spacecraft upward in a slow, steady climb. The astronauts returned to orbit, rejoined their companion in the command module, and began the long journey home. Re-entry into Earth's atmosphere is another precise and unforgiving process. The angle must be exact, too shallow, and the spacecraft skips off the atmosphere back into space. Too steep, and heat builds beyond what the protective shield can withstand. Yet once again, the calculations were correct, the systems functioned, and the mission ended with a safe landing in the ocean. From beginning to end, the entire journey had taken just over a week, yet its impact was far greater than the time it occupied. For the first time in history, humanity had extended its physical presence beyond Earth. The Moon, which had once been an unreachable light in the sky, had become a place where people had walked, worked, and departed again. What followed in the years after that first landing is sometimes overlooked. The missions continued. More astronauts travelled to the Moon. They explored different regions, deployed instruments, and returned with hundreds of kilograms of rock and soil. With each mission, confidence grew. procedures improved, and the extraordinary began, in a quiet way, to feel almost routine. And that word, routine, is important to remember, because making something routine requires repetition, practice, and continuity. It requires teams that work together year after year, refining techniques, solving problems, and passing knowledge from one group to the next. During those years, the infrastructure that supported lunar missions was immense. Thousands of engineers, technicians, scientists, and support staff contributed to every launch. Factories produced components to exacting standards. Testing facilities operated around the clock. Training programs prepared astronauts for every conceivable scenario. It was not just a rocket and a spacecraft. It was an entire ecosystem of people and machines working in careful coordination. While the world watched the astronauts, that vast network worked mostly out of sight, ensuring that every detail, from the smallest valve to the largest engine, performed as expected. And yet, ecosystems do not remain unchanged forever. When priorities shift, when funding declines, when projects end, the networks that sustain them begin to disperse. People retire or move on. Facilities are repurposed or dismantled. Suppliers close or change direction. Knowledge that once flowed easily becomes harder to access. All of that would happen gradually in the years after the final lunar missions. But in those early days, none of that was yet visible. What people saw instead was a sense that the future had opened, that travelling to the moon might become more common, perhaps even ordinary one day. Children grew up believing that by the time they were adults, bases might exist on the lunar surface, and journeys beyond to Mars and farther might follow soon after. Reality, as it often does, unfolded differently. The momentum that had carried humanity to the moon slowed, then paused, and eventually stopped altogether. Understanding why that happened, and why restarting such journeys takes so much time and effort, requires looking more closely at what made those early missions possible in the first place. Because the night the world first watched humans walk on another world was not just a moment of triumph. It was the result of an extraordinary convergence of technology, politics, economics, and determination, all aligned in a way that is rare in history. In the years immediately following that first landing, something subtle but remarkable began to happen. What had once seemed almost unimaginable started to take on the shape of a process. Not an easy one, not a casual one, but a process nonetheless. Rockets were assembled again, crews were trained again, trajectories were calculated again, and one by one, missions departed Earth with a destination that had, until very recently, belonged only to dreams. Making something routine does not mean it becomes simple. It means that the unknowns slowly give way to procedures, that uncertainty is replaced by preparation, and that what once required leaps of faith begins to rely more on experience. That is what the Apollo program accomplished in those few intense years. It transformed lunar travel from a single extraordinary event into a sequence of missions that followed one another with growing confidence. To appreciate how this happened, it helps to look beyond the astronauts themselves and consider the scale of what surrounded them. The Apollo program was not just a series of flights. It was a vast, coordinated effort that stretched across factories, laboratories, launch sites, and training centres. At its peak, hundreds of thousands of people were involved, each contributing a small but essential piece of the whole. Some designed engines capable of producing more thrust than anything built before. Others developed guidance systems that could steer a spacecraft across hundreds of thousands of kilometres with remarkable precision. Still others focused on materials, testing metals and composites that could survive the heat of re-entry or the cold of space. There were teams who studied human physiology, learning how the body reacted to weightlessness, isolation, and confined environments. There were engineers who specialised in communications, ensuring that voices and data could travel across the vast distance between Earth and the Moon. What made the program effective was not just the brilliance of individuals, but the way all these efforts were woven together. Procedures were documented in extraordinary detail. Simulations were conducted again and again, exposing crews and controllers to every conceivable malfunction. Hardware was tested to the point of destruction, not because failure was desired, but because understanding the limits of each component was the only way to ensure reliability. Imagine rehearsing a performance so many times that every movement becomes instinctive. That was, in a sense, what Apollo became. The missions were not improvised journeys into the unknown. They were carefully choreographed sequences, refined through repetition and experience. The early flights in the program played a crucial role in building that experience. Before anyone attempted to land on the moon, astronauts practiced every stage of the journey in space. They tested the command module in Earth orbit. They flew the lunar module separately to ensure it could operate as intended. They practiced docking maneuvers, navigation techniques, and emergency procedures. Each mission added new knowledge, reducing uncertainty and increasing confidence. One of the most important aspects of making lunar travel routine was learning how to operate in orbit around the moon itself. This might sound straightforward, but it required precise calculations and careful execution. The spacecraft had to enter lunar orbit at exactly the right speed and angle. Too fast and it would fly past the moon into deep space. Too slow and it would risk crashing into the surface. Once in orbit, astronauts practiced separating and rejoining the lunar module and command module, refining the techniques that would later be used during actual landings. These preparatory missions were not as dramatic as the landings themselves, but they were essential. They turned theory into practice. They revealed small problems that could be corrected before they became serious. They allowed astronauts and mission controllers to develop a shared rhythm, an understanding of how each phase of the mission unfolded in real time. Another factor that made the Apollo missions increasingly reliable was the way knowledge was shared and accumulated. Engineers and technicians documented everything. Every anomaly, every unexpected reading, every minor adjustment was recorded, analysed and discussed. This created a growing body of experience that informed each subsequent flight. Consider for a moment the process of launching a Saturn V rocket. This enormous machine stood taller than a 30-story building and contained millions of parts. Fueling it alone was a carefully timed sequence, involving cryogenic liquids kept at extremely low temperatures. Pumps, valves, and sensors had to function perfectly. The countdown itself was not merely a dramatic ritual. It was a structured checklist, a methodical progression through hundreds of steps designed to verify that every system was ready. With each successful launch, confidence in the process grew. Engineers became more familiar with the behaviour of the engines. Launch crews refined their procedures. Small inefficiencies were identified and corrected. The act of sending a rocket into space did not become trivial, but it did become more predictable. Training played an equally important role. Astronauts spent countless hours in simulators that recreated every stage of the mission. These simulators were not simple mock-ups. They were sophisticated systems that could mimic malfunctions, forcing crews to respond in real time. Engines could fail, instruments could give misleading readings, communications could be interrupted. By the time astronauts flew in space, they had already encountered many of these scenarios dozens of times in training. This preparation extended beyond the astronauts to the teams on the ground. Mission controllers practiced responding to emergencies, coordinating across multiple consoles, and making decisions under pressure. They learned to trust each other's expertise, to communicate clearly and efficiently, and to remain calm even when confronted with unexpected situations. Over time, this combination of preparation, documentation, and repetition created a kind of institutional memory. The program became not just a collection of individuals, but a system that retained knowledge and improved continuously. As more missions reached the moon, the activities conducted there also became more ambitious. Early landings focused on demonstrating that humans could land safely and return. Later missions carried more equipment, stayed longer, and explored more challenging terrain. Astronauts deployed scientific instruments, drove lunar rovers, and travelled greater distances from their landing sites. These later missions reflected a growing confidence in the reliability of the hardware and the procedures. Engineers understood how the lunar module behaved during descent and ascent. Astronauts were familiar with the peculiarities of moving in low gravity. Mission planners had developed detailed timelines that balanced scientific objectives with the constraints of life support and fuel. At the same time, improvements were being made to the spacecraft themselves. Components were refined, software updated, and operational techniques optimized. The program evolved continuously, learning from each flight. It is important to recognize that this progress did not eliminate risk. Spaceflight remained dangerous, and everyone involved understood that. There were close calls, unexpected problems, and moments when outcomes were uncertain. But the program's strength lay in its ability to learn from these experiences, to adapt, and to move forward with greater understanding. Making lunar travel routine also required a stable and well-funded industrial base. Factories produced engines, tanks, electronics, and structural components in large numbers. Suppliers specialized in particular parts, developing expertise that improved quality and reliability. Testing facilities operated at full capacity, ensuring that each component met rigorous standards. This industrial ecosystem was as vital as the rockets themselves. Without it, the missions could not have continued at the pace they did. Public interest and political support also played a role. The Apollo missions were highly visible, and they captured the imagination of people around the world. This visibility helped sustain the funding and commitment needed to maintain such a large program. Launches were broadcast on television. Newspapers reported on each mission. Astronauts became familiar figures, representing not only scientific achievement, but a broader sense of possibility. For a few years, it seemed that travelling to the moon might become a regular activity, perhaps even the beginning of a permanent human presence beyond Earth. Plans were discussed for longer stays, more extensive exploration, and the development of new spacecraft that could carry larger crews. And yet, beneath this sense of momentum, there were signs that the conditions supporting the program were beginning to change. The urgency that had driven the initial effort began to fade. Other priorities competed for attention and resources. The cost of maintaining such a large infrastructure became more difficult to justify in the absence of a clear and immediate goal. Programs like Apollo depend not only on technology and expertise, but on sustained commitment. When that commitment weakens, the structures that support it gradually begin to dissolve. Factories that once produced rocket components closed or shifted to other work. Engineers and technicians moved on to different projects. The intricate network of suppliers and specialists that had made lunar missions possible began to disperse. At first, these changes were subtle. A contract not renewed here, a facility repurposed there. But over time, the cumulative effect was significant. The ability to build and operate the systems required for lunar missions began to fade, not because the knowledge was lost overnight, but because it was no longer being practiced and refined. This is one of the quiet truths about complex endeavours. Skills that are not used regularly tend to diminish. Procedures that are not repeated become harder to recall. Tools and equipment that are not maintained fall into disrepair. During the years when Apollo missions were flying, the entire system was active and engaged. Engineers solved problems daily. Technicians assembled hardware continuously. Astronauts trained intensively. The knowledge was alive, reinforced by constant application. When the missions ended, that living knowledge began to disperse. Documents and blueprints remained, but they could not fully capture the countless small details that experienced workers carried in their minds. The subtle adjustments, the intuitive understanding of how systems behaved, the practical wisdom gained through years of hands-on work, these were harder to preserve. This gradual fading of capability is one of the reasons returning to the moon today is not simply a matter of repeating what was done before. It is not like taking a machine out of storage and turning it on. It is more like rebuilding an entire craft from scattered pieces, guided by records that are valuable but incomplete. Yet at the time, few people expected that the program would end as soon as it did. There was a sense, during those years of repeated missions, that humanity had crossed a threshold, that travelling to the moon had become part of our reach. That sense of routine, however, depended on a unique convergence of factors: a vast industrial effort, sustained funding, political will, public interest, and a workforce whose experience grew with each mission. When those factors began to change, the routine began to unravel, slowly and quietly, until the launches stopped and the moon returned once again to being a distant place visited only by machines and memories. If you were to stand far enough away from a rocket launch, perhaps watching from several kilometers beyond the launch pad, what you would see might appear almost simple: a tall vehicle standing upright, a plume of flame, a slow, powerful rise into the sky, growing smaller until it becomes only a bright point, and then nothing at all. The entire visible drama might last only a few minutes. Yet what lifts off in those minutes is supported by years of preparation and by an enormous network of people whose work remains largely invisible to the public. The astronauts may become the faces remembered in photographs, and the rocket itself may dominate the images, but behind every launch stands a vast, coordinated effort that begins long before the countdown and continues long after the engines fall silent. It helps, for a moment, to imagine a single launch, not as an event, but as the surface ripple of a much deeper current. Beneath it lies a system involving engineers, technicians, scientists, machinists, programmers, logisticians, safety inspectors, trainers, administrators, and countless others whose names rarely appear in headlines, but whose contributions are essential. During the era of the Apollo missions, this hidden army numbered in the hundreds of thousands. Entire cities were shaped by the industry supporting the program. Factories produced engines, tanks, wiring harnesses, guidance systems, and structural components. Laboratories conducted experiments on materials and fuels. Test facilities fired engines under controlled conditions, pushing them to their limits to ensure they would perform reliably in flight. Each part of a spacecraft passed through many hands before it ever reached the launch pad. Consider something as seemingly simple as a bolt. That bolt had to be made from the right alloy, machined to exact tolerances, inspected for microscopic flaws, and tested to ensure it could withstand the stresses it would encounter. Multiply that process by millions of components, and the scale of the undertaking begins to emerge. The coordination required to bring all these elements together was extraordinary. Components built in different states, sometimes even different countries, had to arrive at the right place at the right time. Schedules were carefully managed, because delays in one part of the system could ripple outward, affecting everything else. Transportation alone was a complex operation. Large rocket stages were moved by specially designed barges or aircraft. Fragile instruments were packed in protective containers and shipped under carefully controlled conditions. Every movement was tracked, documented, and verified. Once components arrived at the launch site, another layer of work began. Technicians assembled the rocket in stages, stacking massive sections with cranes that moved slowly and precisely. Electrical connections were checked and rechecked. Sensors were calibrated. Fuel systems were inspected. At every step, teams followed detailed procedures designed to minimize the chance of error. Testing was constant. Systems were powered on and monitored. Simulated countdowns were conducted. Computers were fed test data to verify their responses. Even after the rocket stood fully assembled, weeks of preparation remained before it was considered ready for launch. While this physical work was underway, another group of specialists focused on the trajectory itself. Orbital mechanics is not something that can be improvised. The path from Earth to the Moon must be calculated with extraordinary precision, taking into account the gravitational influences of both bodies, the rotation of the Earth, and the timing of the launch window. These calculations were not performed once and forgotten. They were refined repeatedly, checked by multiple teams, and verified using independent methods. The goal was not only accuracy but confidence, the assurance that every detail had been examined from multiple angles. At the same time, astronauts were undergoing their own preparations. Training extended far beyond learning how to operate spacecraft systems. They practiced emergency procedures, survival techniques, and the physical tasks they would perform on the Moon. Simulators recreated the interior of the spacecraft, allowing crews to rehearse every phase of the mission. There were also geological training trips, during which astronauts learned how to recognize and collect scientifically valuable samples. These exercises might take place in deserts or volcanic regions, environments chosen because they resembled the lunar surface in certain ways. Scientists accompanied the crews, teaching them how to observe carefully, how to document their findings, and how to think like field researchers. Medical teams monitored the astronauts' health, ensuring they were physically and mentally prepared for the journey. Nutritionists planned diets. Psychologists studied the effects of confinement and isolation. Every aspect of human performance was considered, because in space, small problems can become serious very quickly. Beyond the astronauts and engineers, there were also the mission controllers, the people who would guide the spacecraft from Earth. These teams trained intensively, learning to interpret streams of data, to recognize subtle signs of trouble, and to respond quickly and calmly under pressure. Mission control was organized into specialized roles. One person might monitor propulsion systems, another electrical systems, another life support, and so on. Each specialist focused on a narrow slice of the spacecraft's operation, but all were connected through a structured communication system that allowed information to flow efficiently. Simulations were conducted regularly, sometimes introducing unexpected failures to test the team's readiness. Controllers practiced diagnosing problems, proposing solutions, and coordinating with the astronauts. These exercises could last for hours, replicating the pace and complexity of an actual mission. Meanwhile, safety teams conducted their own reviews, examining every procedure, every component, every potential hazard. Their role was to identify risks and recommend changes to reduce them. This process could be painstaking, involving detailed analysis and sometimes difficult decisions, but it was essential to maintaining confidence in the system. Even the weather played a role in the preparations. Meteorologists monitored conditions not only at the launch site but along the entire flight path. Winds at high altitudes, temperature variations, and the possibility of lightning all had to be considered. Launch windows were chosen carefully, balancing orbital mechanics with environmental conditions. As the launch date approached, the pace of activity increased. Final checks were performed, fueling procedures were rehearsed. The countdown timeline was reviewed in detail, with each step assigned to specific teams and individuals. On the day of the launch, the hidden army was fully engaged. Thousands of people were at work, some in control rooms filled with screens and consoles, others on the launch pad, others still in support facilities handling communications, tracking, and logistics. The fueling process began hours before liftoff. Cryogenic fuels, stored at extremely low temperatures, were pumped into the rocket's tanks. This was a delicate operation, requiring constant monitoring to prevent leaks or temperature fluctuations that could affect performance. As the countdown progressed, teams reported the status of their systems in a steady rhythm. Each confirmation was a small piece of a much larger puzzle, a reassurance that everything was proceeding as planned. From the outside, the final minutes of the countdown might seem tense, but inside the control rooms, the atmosphere was often one of focused concentration. Procedures had been practiced so many times that they unfolded almost automatically. Voices were calm, precise, and measured. When the engines finally ignited, the result was a spectacle of fire and sound. But for the teams involved, it was also the culmination of years of effort. The rocket rose, slowly at first, then faster, carrying with it not only the astronauts but the work of an entire community. And yet, even after the rocket disappeared into the sky, the hidden army continued its work. Tracking stations followed the spacecraft's progress. Engineers analysed data in real time. Mission controllers guided the flight through each phase, from Earth orbit to the journey toward the Moon. This continuous support was essential. Spacecraft do not operate in isolation. They rely on constant communication, on updates and adjustments, on the collective expertise of people on the ground. One of the reasons returning to the Moon today is so challenging is that rebuilding this hidden army takes time. It is not enough to design a new rocket or spacecraft. The entire ecosystem of skills, facilities, and organizations must be reassembled. Factories must be established or retooled. Engineers must be trained. Supply chains must be developed. Procedures must be written, tested, and refined. The knowledge that once existed in living form must be recreated, sometimes by studying old records, sometimes by rediscovering techniques that were once routine. There is also a generational aspect to this process. Many of the people who worked on the Apollo program have retired or passed away. Their experience, their practical insights, and their intuitive understanding of complex systems are difficult to replace. New generations of engineers bring fresh ideas and advanced tools, but they must still build their own experience through years of work and testing. This rebuilding is happening today, quietly and steadily, as new programs prepare for future lunar missions. Teams are being formed, facilities constructed, and systems tested. The hidden army is gathering again, though it looks different now, shaped by modern technologies and new approaches. And as this work continues, it becomes clear that the difficulty of returning to the Moon is not just about rockets or spacecraft. It is about people, about coordination, about the slow and careful process of rebuilding a capability that once existed but was allowed to fade. By the time the Apollo missions were underway, one machine stood at the centre of it all, towering above the launch pad in a way that seemed almost unreal to anyone seeing it for the first time. The Saturn V was not just a rocket. It was, in many ways, the physical expression of an entire era's determination, engineering skill, and willingness to attempt things that had never been done before. To understand why returning to the Moon today is so challenging, it helps to spend some time with this extraordinary machine, because recreating something like it is not as straightforward as simply building another large rocket. Standing more than 110 meters tall, the Saturn V was about the height of a 36-story building. Fully fueled, it weighed nearly 3,000 tons. Numbers like these are impressive, but they only hint at the complexity involved. What made the rocket truly remarkable was not just its size, but the way every part of it worked together to achieve something that had previously been impossible, sending human beings beyond Earth orbit and all the way to the Moon. At the base of the Saturn V were 5 enormous engines known as F1 engines. Each one produced more thrust than any rocket engine built before or since for operational flight. Together, those 5 engines generated about 34 million newtons of thrust at liftoff, enough to lift the fully loaded rocket slowly from the ground and begin its climb into the sky. The word slowly is important here. Despite all that power, the Saturn V did not leap upward like a smaller rocket. For the first few seconds it rose gradually, almost reluctantly, as if testing the air. Only after clearing the launch tower did it begin to accelerate more rapidly. That initial slow rise was not a sign of weakness, but of immense mass. Moving something that heavy required an extraordinary amount of energy. Designing the F1 engines alone was one of the most difficult engineering challenges of the entire program. Burning fuel at such a high rate created intense vibrations and pressures. Early tests revealed a problem known as combustion instability, a phenomenon in which pressure waves inside the engine could grow rapidly, sometimes destroying the engine in a fraction of a second. Engineers had to experiment with different injector designs, baffles, and testing methods to tame this instability. The process took years of trial and error, involving hundreds of test firings and countless refinements. What is striking, looking back, is how much of this work was done without the advanced computer modelling tools available today. Engineers relied heavily on physical testing, building prototypes, observing their behaviour, and making adjustments based on real-world data. It was a method that required patience, resources, and a willingness to learn from failure. Above the first stage of the Saturn V sat the second stage, powered by 5 J2 engines burning liquid hydrogen and liquid oxygen. This stage operated in near-vacuum conditions, where engine performance changes in ways that are difficult to replicate on Earth. The third stage, also powered by a J2 engine, was responsible for pushing the spacecraft out of Earth orbit and onto the trajectory toward the Moon. Each stage of the rocket had a specific role, and the transitions between them had to occur with precise timing. When the first stage finished burning, explosive bolts separated it from the rest of the vehicle. The second stage ignited almost immediately, continuing the climb. Later, the third stage took over, first placing the spacecraft into Earth orbit, and then, after a careful check of systems, reigniting to send it on its way to the Moon. This sequence might sound straightforward when described calmly, but the coordination required was immense. Valves had to open and close at exactly the right moments. Guidance systems had to maintain the correct orientation. Structural components had to withstand the stresses of acceleration, vibration, and temperature changes. One of the reasons the Saturn V was unlike anything built before was the scale at which all of these systems operated simultaneously. Large rockets had been built earlier, but none approached this combination of size, power, and reliability. Achieving that reliability required an enormous testing program. Entire stages were fired on test stands for full-duration burns. Engineers studied how materials expanded and contracted under extreme temperatures. Even small details like the behaviour of wiring insulation or the flow of propellants through pipes were examined carefully. Manufacturing such a rocket was itself a remarkable achievement. Components were built in different parts of the United States and transported to assembly facilities using specially designed aircraft and barges. The logistics involved were complex, requiring careful coordination to ensure that parts arrived in the correct sequence. Another aspect that made the Saturn V unique was the industrial capacity behind it. Factories were dedicated to producing engines, tanks, and structural components at a scale that would be difficult to justify outside of a major national effort. Skilled workers developed specialized techniques, becoming highly experienced in tasks that were performed repeatedly over several years. This concentration of expertise created a kind of momentum. Engineers who had worked on earlier rockets brought their knowledge to the Saturn V. Technicians who had assembled one stage applied what they had learned to the next. The entire workforce became more efficient and more confident as the program progressed. There was also a philosophical difference in the way the Saturn V was designed compared to many modern rockets. The primary goal was to achieve the capability needed to reach the Moon as quickly as possible. Efficiency and reusability, which are major considerations today, were less important than raw performance and reliability. The rocket was expendable, meaning that most of it was discarded during flight. This approach allowed engineers to focus on maximizing thrust and payload capacity, but it also meant that each launch required building an entirely new vehicle. In today's world, where budgets are scrutinized carefully and sustainability is a growing concern, building a completely new rocket for every mission is less appealing. Modern programs often aim to reuse components, reduce costs, and develop systems that can operate over longer periods. These goals introduce new engineering challenges, requiring different designs and testing methods. Returning to the Moon is therefore not simply a matter of recreating the Saturn V exactly as it was. Many of the factories that produced its components no longer exist. The tooling used to shape large fuel tanks and engine parts has been dismantled or repurposed. Suppliers that once specialized in particular materials or processes have moved on to other industries. Even the documentation that survives does not always capture the full story. Blueprints can show dimensions and materials, but they cannot fully convey the experience of the people who built and assembled the parts. There are always small adjustments, techniques learned through practice, and decisions made on the workshop floor that are difficult to record in detail. Another factor is the evolution of technology itself. While modern computers and materials offer significant advantages, they also change the design process. Engineers today might approach the problem differently, using digital simulations and advanced manufacturing methods. This can lead to better performance or lower costs, but it also means that the result will not be identical to the Saturn V. It becomes, in effect, a new machine rather than a replica. The Saturn V was also a product of its time in another sense. It was built during a period when large-scale government programs could mobilize resources quickly and sustain them over several years. The level of funding and political commitment required to develop such a rocket was extraordinary. Replicating that level of focus in a different historical context is not always easy. There is something else worth considering as well. The engineers who designed the Saturn V were working at the edge of what was known at the time. They had fewer precedents to guide them, and in some ways that allowed for bold decisions that might be questioned more carefully today. Modern engineering emphasizes risk reduction, redundancy, and extensive verification. These are valuable practices, but they can also lengthen development timelines and increase costs. All of this helps explain why the Saturn V remains such a remarkable achievement. It was not just a large rocket, but the result of a unique convergence of technology, industrial capacity, political will, and human expertise. Recreating that exact combination decades later is not straightforward. At the same time, it is important to remember that modern rockets are advancing in different directions. Some are designed to be reusable, landing their engines and stages to fly again. Others use new propulsion methods or innovative materials. These developments may not resemble the Saturn V, but they represent progress in their own way, addressing challenges that were less prominent in the past. Still, when people ask why going back to the moon is harder now than it was the first time, the story of the Saturn V provides part of the answer. The machine itself was extraordinary, but the system that supported it was just as important. Rebuilding that system, or creating a new one that achieves the same goals, takes time, resources, and careful planning. As the years passed after the final Apollo missions, the production lines closed, the testing facilities quieted, and the skills associated with building such a rocket began to disperse. Engineers retired or moved to other projects. Companies shifted their focus. The knowledge did not vanish completely, but it became less immediate, less practiced. When the final Apollo mission returned to Earth in December of 1972, there was no single moment when people collectively realized what was slipping away. There was no sudden silence, no dramatic closing of doors, no sense, at least at first, that an era was ending in a way that would be difficult to reverse. Instead, the change came quietly, almost gently, as programs concluded, budgets shifted, and attention moved elsewhere. At the time, it did not necessarily feel like a permanent departure from the moon. Many assumed that human missions beyond Earth orbit would continue in some form, perhaps after a short pause, perhaps with new spacecraft or different goals. The idea that decades might pass before another crew travelled that far seemed unlikely to many observers. Yet history often moves in ways that are only clear in hindsight. What was lost when Apollo ended was not just a series of rockets or spacecraft designs. It was something more complex and more difficult to see, an entire living system of knowledge, experience, infrastructure, and momentum that had made those missions possible. One of the first things to fade was continuity. During the years of Apollo, engineers and technicians were working constantly on lunar missions. Designs were refined, procedures updated, and lessons learned from each flight were applied to the next. There was a rhythm to the work, a steady accumulation of practical experience that made complex tasks feel increasingly familiar. When the mission stopped, that rhythm was broken. Projects were completed, contracts ended, and teams began to disperse. Some engineers moved into other areas of aerospace, working on satellites, aircraft, or the emerging space shuttle program. Others left the field entirely, pursuing different careers or retiring after years of intense work. This gradual dispersal meant that the collective memory of how to build and operate lunar missions began to thin. Documents and technical drawings remained, carefully archived and preserved, but they could not capture everything. Much of what made the program effective existed in the minds of the people who had worked on it, in the habits they had developed, in the small decisions made almost instinctively after years of practice. Consider something as simple as assembling a complex piece of hardware. A blueprint can specify dimensions and materials, but it cannot fully convey the subtle adjustments that experienced technicians make based on touch, sound, or visual cues. These kinds of skills are often learned through repetition and passed on through direct mentorship. When the environment in which they are practiced disappears, the skills themselves become harder to maintain. Another loss was industrial capacity. During the Apollo era, factories were dedicated to producing specific components for lunar missions. Engine production lines, fuel tank manufacturing facilities, and specialized testing centers operated at full capacity. Suppliers developed expertise in materials and processes that were rarely used elsewhere. As demand for these components declined, many of those facilities closed or shifted to other work. Machinery was dismantled or repurposed. Skilled workers moved on. The supply chains that had supported the program, often involving dozens of companies and subcontractors, gradually unraveled. Recreating such an industrial network is not impossible, but it takes time. New facilities must be built or adapted. Workers must be trained. Quality control systems must be established and refined. All of this requires investment and patience, and it cannot be accomplished overnight. There was also a change in focus within the space program itself. After Apollo, attention turned toward developing spacecraft that could operate in Earth orbit for longer periods. The Space Shuttle, which first flew in 1981, represented a different philosophy of spaceflight. It was designed to be reusable, to carry large payloads, and to support scientific research and satellite deployment. This shift brought many benefits, but it also meant that expertise in deep space missions was no longer the primary priority. Engineers concentrated on solving different problems, such as re-entry heating for winged vehicles, the challenges of refurbishing reusable components, and the logistics of operating a space station. Over time, the skills associated with travelling beyond Earth orbit became less common. Navigation techniques, mission planning strategies, and operational procedures specific to lunar missions were no longer practiced regularly. They remained documented, but documentation alone cannot replace experience. Another factor that contributed to the loss of capability was the passage of time itself. The Apollo program had been driven by a sense of urgency, a determination to achieve a specific goal within a defined time frame. That urgency created a momentum that carried projects forward rapidly. When that sense of urgency faded, so did the momentum. Without a clear and immediate objective, large-scale programs became more difficult to justify. Funding levels declined, and the infrastructure required for lunar missions became harder to sustain. Public attention also shifted. The first landing on the moon had captured the imagination of millions, but as the missions continued, they began to feel less novel to some audiences. Television broadcasts still drew viewers, but the sense of wonder that accompanied the earliest flights gradually softened. By the time of the later missions, some networks even chose not to broadcast the launches live, reflecting a perception that the extraordinary had become familiar. This change in public interest influenced political decisions, which in turn affected funding and priorities. Large programs depend not only on technical feasibility, but on sustained support from governments and societies. When that support wanes, even the most ambitious projects can be scaled back or concluded. There is also a subtle psychological dimension to what was lost. During the Apollo era, the idea of travelling to the moon was part of the present. Engineers, astronauts, and mission controllers worked with a shared understanding that this was what they did, that lunar missions were an ongoing reality. When the missions ended, that sense of immediacy disappeared. The moon became, once again, a distant place, visited only in memory and in the pages of history books. The practical mindset of preparing for the next launch was replaced by reflection on what had already been achieved. This shift in perspective can influence the way organizations think and plan. When a capability is active, maintaining it feels natural. When it becomes dormant, reactivating it requires deliberate effort and long-term commitment. There were also technical challenges associated with preserving hardware and facilities. Large test stands, launch infrastructure, and specialized equipment require regular maintenance to remain operational. When budgets are reduced and programs end, maintaining such facilities becomes difficult. Some were decommissioned, others dismantled, and a few preserved as historical sites rather than active components of a working system. The knowledge embedded in these facilities, the familiarity of technicians with specific tools and procedures, gradually faded as well. Even when buildings remained standing, the expertise required to use them effectively was no longer present in the same way. Yet it's important to recognize that not everything was lost. Many of the scientific and engineering lessons learned during Apollo continued to influence later programs. Data from lunar samples contributed to our understanding of the moon's formation and the early history of the solar system. Technologies developed for the program found applications in other fields, from computing to materials science. The legacy of Apollo also inspired new generations of engineers and scientists. The images of astronauts walking on the moon, the recordings of their voices, and the stories of the missions became part of the cultural memory of humanity. For many people, those missions sparked a lifelong interest in space and exploration. Still, inspiration alone does not maintain infrastructure or preserve industrial capacity. Rebuilding the ability to send humans to the moon requires more than remembering how it was done. It requires reconstructing the networks of people, facilities, and expertise that once made it possible. This process has been underway for years, involving new programs, new spacecraft, and new approaches to exploration. Engineers study the records of Apollo, learning from both its successes and its challenges. Modern tools allow for more precise simulations and new materials offer improved performance, but the fundamental complexity of lunar missions remains. One of the most striking aspects of this rebuilding effort is how much of it involves rediscovering practical knowledge. Teams must relearn how to manufacture certain components, how to test systems under conditions that simulate the environment of space, and how to coordinate large, multidisciplinary projects over long periods. In some cases, engineers have found that reproducing older designs exactly is not feasible, either because materials are no longer available or because manufacturing techniques have changed. This requires adapting the designs, finding new solutions that achieve the same objectives while meeting modern standards. The passage of time has also brought new expectations. Safety standards are more stringent. Environmental regulations are more comprehensive. Public scrutiny is greater. All of these factors contribute to longer development timelines and more extensive testing, which, while beneficial in many ways, also make large projects more complex to execute. As these efforts continue, it becomes clear that what was lost when Apollo ended was not just hardware or funding, but a living, evolving capability that depended on continuous practice and sustained commitment. Rebuilding that capability is not a matter of simply turning the clock back. It is a process of creating something new, informed by the past but shaped by the realities of the present. Something curious happens when a complex activity is no longer practiced for a long time. The written records remain. The diagrams remain. The reports and technical manuals sit in archives, sometimes carefully preserved, sometimes slowly aging in storage rooms or converted into digital files. On paper, it can appear that nothing essential has been lost, and yet, when people try to repeat the work years later, they often discover that knowledge is not the same thing as information. This quiet gap between what is written down and what is actually understood is sometimes called the vanishing knowledge problem. It is not unique to spaceflight. Historians have seen it in many fields. Ancient techniques for making certain materials or constructing particular structures have been rediscovered only after long periods of trial and error, even when records existed. The instructions survived, but the deeper understanding of how to interpret them had faded. In the case of the Apollo program, the scale of this problem was unusually large, because the systems involved were so complex, and because so much of the expertise existed in the minds and habits of the people who built and operated them. During the years when lunar missions were active, engineers and technicians interacted constantly with the hardware. They knew how systems behaved not only under ideal conditions, but in subtle, imperfect situations. They recognized patterns in the way instruments responded, in the sounds of pumps and valves, in the feel of controls and the timing of procedures. Much of this knowledge was never formally documented because it seemed obvious to those who used it every day. Imagine learning to play a musical instrument. A book can explain where to place your fingers and how to read notes, but it cannot fully convey the sense of pressure, timing, and subtle adjustments that experienced musicians develop over years of practice. That knowledge lives in muscle memory and intuition, and it fades if not used. Spacecraft engineering, though very different in nature, shares this characteristic. There are countless small details that experienced workers understand instinctively. How tightly to fasten a particular fitting, how a material behaves under stress, how to recognize a warning sign before it becomes a problem. These are things that are learned through repetition and observation, often passed from one generation to the next through direct mentorship. When the Apollo program ended, many of the people who held this practical knowledge moved on to other work or retired. The continuity of mentorship was interrupted. New engineers entering the field studied the documentation, but they did not have the same opportunity to learn directly from those who had built and flown the original hardware. Over time, this created a situation in which the technical information existed, but the living knowledge that gave it context had begun to fade. There were also challenges related to the way information was stored. Much of the documentation from the Apollo era was created using methods that seem unfamiliar today. Drawings were often done by hand. Data was recorded on paper or magnetic tapes. Some records were archived in formats that later became difficult to access as technology changed. In some cases, engineers working decades later discovered that certain material specifications or manufacturing techniques were described only briefly, with the expectation that readers would already understand the details. When those readers were no longer available to ask questions, interpreting the instructions became more difficult. Even terminology can change over time. Words and abbreviations that were common in one era may not be used in the same way later. This can lead to misunderstandings or the need for careful translation between different generations of technical language. Another aspect of the vanishing knowledge problem involves tools and equipment. During the Apollo era, factories and workshops were equipped with machinery designed for specific tasks. Workers became skilled at using those tools, developing techniques that were not always written down. When the tools were dismantled or replaced, the associated skills faded as well. Recreating those skills sometimes requires rebuilding the tools themselves or developing new methods that achieve the same results. This process can be time-consuming and requires experimentation, because even small differences in manufacturing techniques can affect the performance of critical components. There is also a psychological dimension to knowledge that is difficult to preserve. Teams that work together over long periods develop a shared understanding, a kind of collective intuition about how systems behave and how to solve problems. This understanding is reinforced by daily interaction, by conversations in hallways and workshops, by informal exchanges of ideas. When such teams disperse, that shared intuition disappears. New teams must build their own understanding from the ground up, a process that takes time and experience. One example often mentioned by engineers involves the production of the F1 engines used in the Saturn V rocket. While the general design of the engine was well documented, reproducing it exactly would be extremely difficult today, not only because of changes in materials and manufacturing methods, but because many of the practical details of how it was built existed primarily in the experience of the workers who assembled it. This does not mean that modern engineers are less capable. On the contrary, they have access to powerful tools, advanced materials, and sophisticated testing methods. But they must still rediscover or reinvent certain aspects of the process, and that takes time. Another factor contributing to the vanishing knowledge problem is the natural evolution of technology. As new methods and tools become available, older techniques may be abandoned. Over time, fewer people remain who are familiar with those older methods, and the ability to use them effectively diminishes. In some cases, engineers deliberately choose not to replicate older designs exactly, because modern approaches can offer advantages in efficiency, safety, or cost. This is often the right decision, but it also means that rebuilding a capability becomes a process of innovation rather than simple replication. There is a quiet irony in this. The progress that makes new achievements possible can also make it hard to repeat certain past accomplishments in exactly the same way. The vanishing knowledge problem also affects operational procedures. During the Apollo missions, mission controllers and astronauts developed routines that allowed them to respond quickly and effectively to unexpected situations. These routines were shaped by experience, by the lessons learned from simulations and real missions. When lunar missions stopped, the opportunity to practice these procedures disappeared. While the general principles of mission control remain the same, the specific experience of managing deep space missions became less common. Rebuilding that experience requires new missions, new simulations, and time for teams to develop confidence in their abilities. Another subtle aspect of knowledge that fades over time is the sense of scale involved in large projects. During the Apollo era, thousands of people were accustomed to working on a program of enormous scope. They understood how to coordinate complex schedules, how to manage large budgets, and how to integrate the work of many different organizations. As the focus of space programs shifted to smaller or differently structured projects, fewer people gained experience managing efforts of that magnitude. Rebuilding that capacity involves not only technical challenges, but organizational ones, learning how to coordinate large teams and maintain momentum over many years. Despite these challenges, the vanishing knowledge problem is not insurmountable. Engineers and historians have worked diligently to preserve as much information as possible. Documents have been digitized, interviews have been conducted with people who participated in the Apollo program, capturing their insights and recollections. Museums and archives maintain hardware and records that provide valuable references for modern researchers. New generations of engineers are also bringing fresh perspectives and innovative approaches. They are not simply trying to recreate the past, but to build on it, using modern tools and techniques to achieve similar or greater capabilities. This process of rediscovery and reinvention is part of the natural cycle of technological progress. Knowledge may fade in one form, but it can be rebuilt in another, often with improvements that were not possible before. Still, the time required to rebuild that knowledge helps explain why returning to the moon is not as quick or straightforward as some might expect. It is not a matter of opening an old manual and following the steps. It is a process of learning, testing, and gradually rebuilding confidence in systems that must operate flawlessly in one of the most unforgiving environments imaginable. As these efforts continue, it becomes clear that the challenge is not only technical, but human, involving the transmission of skills, the rebuilding of experience, and the careful reconstruction of a capability that once existed, but was allowed to rest for many years. As the decades passed after the last journeys to the moon, rockets did not disappear. In fact, they continued to improve in many ways. Satellites became more capable, interplanetary probes travelled farther than ever before, and new launch vehicles were developed with better computers, stronger materials, and more precise guidance systems. From a distance, it might seem that returning to the moon should therefore be easier. If rockets today are more advanced, why not simply point one toward the moon and repeat what was done before? The answer lies in understanding that modern rockets, while powerful and sophisticated, were not designed with exactly the same goals in mind as the vehicles of the Apollo era. They reflect different priorities, different engineering philosophies, and different economic realities. And those differences matter more than they might appear at first glance. One of the most important changes is the emphasis on efficiency and cost. During the Apollo program, the primary objective was clear and urgent: reach the moon before the end of the decade. Achieving that goal required enormous resources, and for a few years, those resources were provided on a scale rarely seen in peacetime projects. Rockets were designed to maximize performance, even if that meant discarding large portions of the vehicle during each launch. Modern space programs often operate under very different constraints. Budgets are carefully scrutinized, and there is strong pressure to reduce the cost of each launch. This has led to a focus on reusability, the idea that parts of a rocket can be recovered, refurbished, and flown again. Reusable boosters have become increasingly common, landing on platforms or returning to launch sites after completing their work. This approach offers clear advantages. Reusing major components can reduce costs and allow more frequent launches. It also encourages designs that are durable and easier to maintain, but it also changes the structure of the rocket and the way missions are planned. A reusable booster may be optimized for returning safely to Earth rather than for maximizing payload to deep space. Trade-offs must be made, balancing performance, durability, and cost. Another difference lies in the types of missions most rockets have been designed to support over the past several decades. Many launch vehicles have focused on delivering satellites to Earth orbit, a task that requires substantial energy but far less than sending a crewed spacecraft to the moon. Reaching low Earth orbit is only the first step in a lunar mission. Additional propulsion is needed to leave Earth's gravitational influence and travel the hundreds of thousands of kilometers to the moon. Some modern rockets are capable of providing that additional energy, but many are not, at least not without multiple launches and complex assembly of spacecraft in orbit. This introduces new challenges in coordination, timing, and risk management. The evolution of materials and manufacturing methods has also influenced rocket design. Engineers today have access to advanced alloys, composites, and manufacturing techniques such as 3D printing. These technologies allow for lighter structures, more intricate components, and improved performance in many areas. However, they also require new testing methods and new ways of verifying reliability. Designing a rocket is not only about making it powerful, it is also about ensuring that every part functions correctly under extreme conditions. New materials and processes must be studied carefully, sometimes for years, before they are trusted in critical systems. This careful validation contributes to longer development timelines, even as it leads to safer and more efficient designs. Computers and software have advanced dramatically since the 1960s, and this has changed the way rockets are controlled and monitored. Guidance systems are now far more capable, able to process vast amounts of data and make precise adjustments in real time. Simulation tools allow engineers to model complex interactions before hardware is built. These advances are powerful, but they also introduce new layers of complexity. Software must be written, tested, and verified to an extraordinary degree of reliability, especially in crewed missions where lives depend on flawless performance. Verifying millions of lines of code can take as much effort as building physical components, and small errors can have significant consequences. There is also a cultural and procedural difference in the way modern space programs approach risk. During the Apollo era, the urgency of the goal and the spirit of exploration led to a willingness to accept higher levels of risk than would be considered acceptable today. That does not mean safety was ignored. engineers worked tirelessly to reduce dangers wherever possible. But the balance between speed and caution was different. Today, the expectations placed on crewed missions are even more stringent. Extensive testing, redundancy, and certification processes are required before astronauts are allowed to fly. These measures increase safety, but they also increase the time and cost required to develop and operate spacecraft. Another important factor is that modern rockets are often designed as part of broader, long-term strategies rather than single-focused programs. They may be intended to support a variety of missions, from satellite launches to deep space exploration. This versatility can be an advantage, but it also means that the vehicles are not always optimized for a specific task like lunar travel in the way the Saturn V was. International collaboration has also become more common. Space exploration today often involves partnerships between multiple countries and organizations. This cooperation brings valuable expertise and shared resources, but it also requires coordination across different regulatory systems, engineering standards, and management structures. Decision-making can take longer, and development timelines may be influenced by diplomatic as well as technical considerations. Even the infrastructure surrounding launches has changed. Modern launch facilities must meet updated environmental regulations and safety requirements. Fuel handling, waste management, and noise mitigation are all subject to stricter oversight than in the past. These considerations are important for protecting communities and ecosystems, but they add additional layers of planning and compliance. There is also the matter of expectations. When the first lunar missions were undertaken, the world had never seen anything like them. Every step forward was new, and there was a sense of discovery even in small achievements. Today, audiences are more familiar with spaceflight, and there is often an expectation that technology should progress quickly and smoothly. In reality, developing new rockets and spacecraft remains a complex and time-consuming process, regardless of advances in computing and materials. One of the most interesting aspects of modern rocket development is the diversity of approaches being pursued. Some organizations are building extremely large rockets designed to carry heavy payloads beyond Earth orbit, while others are focusing on modular systems that can be assembled in space. Still others are exploring new propulsion methods or reusable spacecraft that can operate for extended periods. This diversity reflects a broader shift in the goals of space exploration. Returning to the Moon is no longer seen as an endpoint, but as part of a larger journey that may include building sustainable habitats, conducting long-term scientific research, and eventually travelling to Mars. Designing systems for these purposes requires thinking beyond a single mission, considering how spacecraft and infrastructure will be used over many years. All of these factors contribute to the reality that modern rockets, while powerful and technologically advanced, are not identical to those that carried astronauts to the Moon in the past. They are shaped by different priorities, different technologies, and different visions of the future. This does not mean that the capability to reach the Moon has been lost. Rather, it is being rebuilt in a new form, one that reflects the lessons of the past and the possibilities of the present. The process takes time, because each new design must be tested, refined, and proven reliable before it can carry human beings safely beyond Earth orbit. Progress often brings an interesting kind of complication. When we become better at something, we also become more aware of how much can go wrong. We learn from past accidents, from close calls, from the small details that once went unnoticed. And as that awareness grows, so do the expectations placed on every new endeavour. This is especially true in spaceflight, where the margin for error is almost non-existent, and the consequences of failure are profound. Returning to the Moon today involves not only rebuilding technology and knowledge, but also meeting safety standards that are far more demanding than those of the past. This is not because earlier engineers were careless or indifferent. On the contrary, they worked with extraordinary dedication to protect the lives of astronauts, but the understanding of risk and the systems used to manage it have evolved significantly over the decades. One of the most important differences is the way risk is analysed. During the Apollo era, Engineers relied on the best tools available to them, but many of the analytical methods used today did not yet exist. Computer modelling was limited. Large-scale simulations were more difficult to perform. Some risks could only be understood through physical testing, which sometimes meant learning from failures that occurred during development. In the years since then, the field of safety engineering has expanded dramatically. Engineers now use detailed probabilistic risk assessments, modelling thousands of possible failure scenarios and estimating their likelihood. Systems are designed with multiple layers of redundancy, so that the failure of one component does not necessarily lead to the loss of the entire mission. These methods have improved safety, but they also make development more complex. Each additional layer of redundancy requires extra components, extra testing, and careful integration. Verifying that all these systems work together correctly can take years, especially for spacecraft intended to carry human beings far beyond Earth. There is also a deeper cultural change that has taken place. Society's tolerance for risk, particularly in publicly funded programs, has shifted. In the early days of space exploration, astronauts were widely regarded as pioneers, people who knowingly accepted extraordinary dangers. The public admired their courage and understood that exploration carried inherent risks. Today, expectations are different. While astronauts are still respected for their bravery, there is a stronger emphasis on ensuring that every reasonable precaution has been taken. Accidents are examined in great detail, and lessons learned are incorporated into future designs. This approach has undoubtedly saved lives, but it also means that new spacecraft must undergo more extensive testing and certification before they are approved for flight. Historical events have played a role in shaping these attitudes. Accidents such as the loss of spacecraft and crews during various space programs led to comprehensive investigations and sweeping changes in safety procedures. Each investigation produced recommendations, and over time these recommendations accumulated, creating a framework of standards and practices that must now be followed. These standards affect every aspect of spacecraft design and operation. Materials must be tested under a wide range of conditions to ensure they behave predictably. Electrical systems must be designed to prevent fires or short circuits. Life support systems must function reliably for extended periods, even if individual components fail. Testing has become more rigorous as well. Components are subjected to vibration tests that simulate the intense forces of launch. Thermal tests expose hardware to the extreme temperatures of space. Vacuum chambers replicate the near-empty environment beyond Earth's atmosphere. These tests are essential, but they require time and specialized facilities. Another aspect of modern safety standards is documentation. Every decision, every test result, and every modification must be recorded and reviewed. This creates a detailed trail of evidence demonstrating that systems meet the required criteria. While this level of documentation improves accountability and reliability, it also adds to the workload of engineers and project managers. Software, too, has become a major focus of safety efforts. Modern spacecraft rely heavily on computer systems to control engines, manage power, and monitor environmental conditions. Ensuring that this software operates flawlessly is a formidable task. Engineers must test millions of lines of code searching for errors that could cause unexpected behavior. Unlike mechanical components, software failures can be subtle and difficult to detect. A small error in logic or timing can have significant consequences. As a result, software verification has become one of the most time-consuming aspects of spacecraft development. There is also the challenge of integrating new technologies. Advances in materials, electronics, and propulsion offer many benefits, but each new technology introduces uncertainties that must be carefully studied. Engineers must demonstrate not only that a new component works, but that it will continue to work reliably over the entire duration of a mission. This cautious approach sometimes creates the impression that progress has slowed, but in reality, it reflects a deeper commitment to safety. The goal is not merely to reach the moon, but to do so in a way that minimizes risk to the greatest extent possible. One of the paradoxes of progress is that greater knowledge often leads to greater caution. When engineers understand more about the ways systems can fail, they design additional safeguards to prevent those failures. Each safeguard adds complexity, and managing that complexity requires more testing, more analysis, and more time. Another factor contributing to longer timelines is the need for independent reviews. Modern space programs often involve multiple organizations, each responsible for verifying different aspects of the design. These reviews provide valuable oversight, but they also extend the development process as findings are discussed and recommendations implemented. Even operational procedures are affected by evolving safety standards. Astronaut training programs are more comprehensive, covering a wider range of scenarios and contingencies. Mission timelines include additional checks and verifications. Launch decisions are made only after careful consideration of weather, technical status, and potential risks. These measures may seem cautious, but they reflect the understanding that spaceflight remains inherently dangerous. The environment beyond Earth is unforgiving, and even small errors can have serious consequences. The effort invested in safety is an acknowledgement of that reality. It is also worth noting that safety standards do not exist in isolation. They are influenced by broader societal values and expectations. As technology has advanced in other fields, people have grown accustomed to high levels of reliability and precision. This expectation extends to space exploration, where failures are often highly visible and widely reported. At the same time, there is a growing recognition of the importance of sustainability and long-term planning. Missions are designed not only to succeed in the short term, but to contribute to a broader program of exploration. This perspective encourages careful planning and thorough testing, even when it means moving more slowly. All of these factors contribute to what might be called the paradox of progress. The very advances that make spaceflight safer and more reliable also make it more complex and time-consuming to develop new systems. Returning to the Moon today involves navigating this landscape of rigorous standards, detailed analyses, and careful verification. Yet this is not a negative development. The emphasis on safety reflects a deep respect for the lives of astronauts and the immense effort required to send them into space. It represents a commitment to learning from the past and applying those lessons to the future. As engineers and scientists continue working toward new lunar missions, they do so with tools and knowledge that earlier generations could only imagine, but they also carry the responsibility of ensuring that every system, every procedure, and every decision meets the higher standards of reliability. This careful, methodical approach may take longer than the rapid pace of earlier programs, but it is part of a broader evolution in how humanity explores space. There is another force, quieter than engines and less visible than spacecraft, that shapes every journey into space. It does not roar at liftoff or glow in the night sky, yet without it, no rocket ever leaves the ground. That force is the steady flow of resources, guided by decisions made in offices, parliaments, and meeting rooms far from launch pads. Money and politics may sound less romantic than astronauts and rockets, but they are as essential to space exploration as fuel and guidance systems. To understand why returning to the Moon has taken so long, it helps to step back and look at the broader landscape in which the original missions took place. The Apollo program was not only a scientific or engineering effort, it was also a political project shaped by the circumstances of its time. In the early 1960s, the world was divided by intense geopolitical competition. The United States and the Soviet Union were engaged in a rivalry that extended into nearly every field, from military technology to cultural influence. Space became one of the most visible arenas of this competition. Each milestone carried symbolic weight, demonstrating technological capability and national prestige. When the decision was made to send humans to the Moon, it was driven in part by this sense of urgency. Achieving such a goal was seen not only as a scientific triumph, but as a statement about the strength and ingenuity of a nation. This urgency had a powerful effect on funding and organisation. Resources were allocated on a scale that would be difficult to justify under ordinary circumstances. At its peak, the Apollo program consumed a significant portion of the United States federal budget. Entire industries expanded to support it. Universities trained engineers and scientists in large numbers. Facilities were built, equipment purchased, and contracts awarded at a pace rarely seen before or since. This concentration of resources created momentum. Projects moved quickly because the funding was available and the objective was clear. When obstacles appeared, additional teams and equipment could often be brought in to address them. The sense of a shared national goal helped sustain this effort, even when challenges arose. But large programs are rarely permanent. As the 1960s came to an end, the political and social landscape began to change. The initial objective, landing humans on the moon, had been achieved. The urgency that had driven the program began to fade. Other concerns demanded attention, both domestically and internationally. Governments must always balance competing priorities. Funding allocated to one program is funding that cannot be used elsewhere. Infrastructure, education, healthcare, and many other needs all require resources. Space exploration, inspiring and valuable as it is, must compete within this broader context. As public interest in lunar missions declined and political priorities shifted, budgets were reduced. Plans for additional missions were scaled back or cancelled. The vast infrastructure that had supported Apollo became increasingly difficult to maintain without the same level of financial support. It's important to recognise that this was not simply a matter of losing interest in space. The focus of exploration began to change. Programs were developed to study Earth from orbit, to deploy communications and weather satellites, and to build reusable spacecraft that could operate more frequently. These initiatives required significant investment and offered practical benefits that were easier to explain to the public. The development of the space shuttle, for example, represented a new vision of spaceflight. Instead of sending humans on occasional journeys beyond Earth orbit, the goal was to create a system that could operate more regularly, supporting scientific research and commercial activities in low Earth orbit. This shift influenced how resources were allocated and how long-term plans were shaped. At the same time, the political environment surrounding large government projects was evolving. Public expectations about transparency, accountability, and fiscal responsibility were increasing. Large expenditures were scrutinized more closely, and programs had to justify their costs in greater detail. This change in expectations affected not only funding levels but also the way projects were managed. Decision-making processes became more complex, involving multiple layers of review and oversight. While these measures improved accountability, they also made it more challenging to move quickly. International relations also played a role in shaping the path of space exploration. During the Apollo era, the space race was largely a competition between two superpowers. In the decades that followed, cooperation became more common. Joint missions, shared research, and multinational projects emerged, reflecting a recognition that exploring space could be a collective endeavour rather than a purely national one. International cooperation brings many advantages. It allows costs to be shared, expertise to be pooled, and diverse perspectives to be included. The International Space Station is one of the most visible examples of this approach, involving contributions from multiple countries over many years. However, cooperation also introduces new complexities. Agreements must be negotiated. Responsibilities must be divided. Technical standards must be harmonized. Decisions that might once have been made by a single organization now require coordination among many partners. These processes take time, and they can influence the pace at which new programs move forward. Returning to the moon in the 21st century is not simply a matter of repeating a national effort from the 1960s. It often involves building partnerships, aligning goals, and coordinating schedules across different agencies and governments. Another factor influencing the long road back to the moon is the changing role of private industry. In recent years, commercial companies have become increasingly involved in spaceflight, developing launch vehicles, spacecraft, and supporting technologies. This shift has brought new energy and innovation to the field, as well as new business models that aim to reduce costs and increase flexibility. The involvement of private companies has also changed how programs are structured. Governments may now act as customers rather than sole operators, purchasing services from commercial providers. This approach can encourage competition and efficiency, but it also requires new forms of coordination and contract management. Developing new spacecraft and launch systems under these arrangements still requires substantial investment and careful planning. Testing, certification, and integration with existing infrastructure remain complex tasks, regardless of whether the hardware is built by government agencies or private firms. Economic cycles also play a role in shaping long-term projects. Space programs often span decades, and during that time, economies can expand and contract, political leadership can change, and priorities can shift. Maintaining consistent funding and support over such long periods is a significant challenge. Public perception influences these decisions as well. Space exploration inspires many people, but it must also demonstrate tangible benefits to sustain broad support. Scientific discoveries, technological innovations, and economic opportunities all contribute to making the case for continued investment. In recent years, interest in returning to the moon has grown again, driven by new scientific questions and the possibility of using the moon as a stepping stone for deeper exploration. Water ice discovered in permanently shadowed craters, for example, offers the potential for producing fuel and supporting long-term human presence. These discoveries have renewed the sense that the moon is not only a destination but a place where important research and development can occur. Programs aimed at returning humans to the lunar surface are now underway, involving both government agencies and commercial partners. These initiatives are ambitious, seeking not only to land astronauts but to establish a sustainable presence that can support ongoing exploration. Building such a presence requires careful planning and substantial resources. Habitats, power systems, transportation infrastructure, and scientific equipment must all be developed and delivered. Each of these elements involves its own technical and financial challenges. Unlike the Apollo missions, which focused on reaching the moon as quickly as possible, modern programs aim to create systems that can operate over many years. This long-term perspective influences design decisions, budgets, and timelines. It also requires a level of international cooperation and political stability that can be difficult to maintain. The pace of progress may sometimes feel slow, but it reflects the complexity of the goals being pursued. Returning to the moon today is not just about repeating a historic achievement. It is about building the foundation for a sustained human presence beyond Earth, a step that carries implications far beyond a single mission. Looking back, it becomes clear that the road away from the moon was shaped by a combination of changing priorities, economic realities, and evolving visions of what space exploration should accomplish. The road back is shaped by similar forces, guiding decisions about funding, partnerships, and long-term strategy. These forces are less visible than rockets rising into the sky, but they are just as powerful. They determine which projects move forward, how quickly they progress, and what goals they pursue. Understanding their influence helps explain why returning to the moon is not simply a technical challenge, but a complex undertaking shaped by the choices of societies and the passage of time. Reaching the moon is only one part of the challenge. The other quieter difficulty lies in preparing everything that must function once you arrive. A rocket can carry people across the distance, but the moment a spacecraft settles onto the lunar surface, an entirely different set of demands begins. The moon is not merely far away. It is an environment that behaves in ways that are unfamiliar, sometimes unforgiving, and often subtly different from what engineers encounter anywhere on Earth. When the Apollo missions were planned, much of this was unknown. Scientists had studied the moon through telescopes, measured its gravity, and analysed the faint reflections of radar signals. But many practical details remained uncertain. Would the surface be firm enough to support a spacecraft? Or would it behave like deep powder? How abrasive was the dust? How would equipment function in an environment with no atmosphere, extreme temperature swings, and reduced gravity? Those early missions answered many of these questions, but they also revealed new ones, and they left behind an important lesson. Operating on the Moon requires tools, vehicles, and systems designed specifically for that environment. Equipment built for Earth cannot simply be adapted with minor changes. It must be rethought from the ground up. One of the most striking features of the Moon is the absence of atmosphere. This affects nearly everything. Without air, there is no natural cooling through convection, the process by which heat is carried away by moving air. On Earth, machines often rely on airflow to regulate temperature. Fans circulate air around electronics, engines radiate heat into the surrounding environment, and cooling systems are designed with the expectation that air will help carry heat away. On the Moon, none of that works in the same way. Heat must be managed through radiation and conduction, which require careful design and precise materials. Electronics must be protected from overheating during the long lunar day, when sunlight can raise surface temperatures well above the boiling point of water, and from freezing during the long lunar night, when temperatures plunge far below anything experienced in most places on Earth. These temperature extremes create challenges not only for electronics, but for structural materials as well. Metals expand and contract as they heat and cool. Seals and joints must remain airtight despite repeated cycles of expansion and contraction. Lubricants that function well on Earth may evaporate or become brittle in vacuum and cold. During the Apollo era, engineers developed solutions to many of these problems, but much of that hardware was designed for short missions lasting only a few days on the surface. Modern plans often involve longer stays, perhaps weeks or months, and eventually permanent or semi-permanent habitats. Designing equipment that can operate reliably over such extended periods requires new approaches, new materials, and extensive testing. The lunar surface itself presents another challenge. The dust that covers much of the Moon is unlike any soil on Earth. It is extremely fine, almost like powder, but its particles are sharp and jagged because they have not been worn smooth by wind or water. This dust clings to surfaces, infiltrates mechanisms, and can damage seals and moving parts. Astronauts during the Apollo missions quickly discovered how persistent this dust could be. It stuck to their suits, coated equipment, and even found its way into the cabin of the lunar module. Some reported that it had a distinctive smell, carried inside on their gear. Over time, engineers realized that any long-term presence on the Moon would require improved methods for managing dust, from airlocks designed to keep it outside to materials that resist its abrasive effects. Building vehicles for movement across the lunar surface is another area where challenges emerge. The reduced gravity, about 1/6 that of Earth, changes how vehicles behave. Wheels must be designed to provide traction without digging too deeply into the soil. Suspension systems must account for the lower weight, but still handle uneven terrain and the stresses of movement. The lunar rovers used in the later Apollo missions were remarkable machines, lightweight and foldable so they could be carried to the Moon and deployed by astronauts. They performed well, but they were designed for limited use over relatively short distances. Future exploration may require vehicles capable of travelling much farther, carrying heavier loads, and operating autonomously or semi-autonomously for extended periods. Power generation is another essential consideration. On Earth, power is often readily available through electrical grids or fuel supplies. On the Moon, energy must be generated locally, usually through solar panels or, in some cases, nuclear power systems. Solar energy is abundant during the lunar day, which lasts about 2 Earth weeks, but the equally long lunar night presents a significant challenge. Systems must either store enough energy to last through the darkness, or rely on alternative power sources. Energy storage technologies have improved greatly in recent decades, but providing reliable power for long-duration missions remains a complex problem. Batteries must be efficient, durable, and capable of operating in extreme temperatures. Power management systems must distribute energy carefully, ensuring that critical systems remain operational even when resources are limited. Life support systems, too, must be redesigned for longer missions. Providing air, water, and temperature control for astronauts on the Moon involves more than simply carrying supplies from Earth. For extended stays, recycling systems become essential, recovering water from humidity and waste, filtering air, and maintaining stable environmental conditions within habitats. Some plans even involve using local resources to reduce the need for supplies from Earth. Water ice discovered in certain lunar regions could potentially be processed into drinking water, oxygen, and even rocket fuel. This concept, known as in situ resource utilization, offers exciting possibilities, but it also requires developing new technologies capable of operating reliably in the harsh lunar environment. Landing systems present another set of challenges. The Apollo lunar module was designed for specific landing sites and mission profiles. Modern missions may aim for different regions, including areas near the lunar poles where lighting conditions and terrain vary significantly. Precision landing technologies must be refined to ensure that spacecraft can reach these sites safely. Navigation and communication systems must also be adapted. The Moon's far side, for example, never faces Earth, making direct communication impossible without relay satellites. Establishing reliable communication networks around the Moon is an important step towards sustained exploration. Even something as simple as walking becomes more complicated on the Moon. Spacesuits must protect astronauts from vacuum, temperature extremes, and radiation, while allowing enough flexibility for movement and work. The suits used during Apollo were effective but limited in mobility and durability. Designing new suits that can support longer missions and more demanding activities is an ongoing effort. Radiation is another factor that cannot be ignored. Without a protective atmosphere or magnetic field like Earth's, the Moon is exposed to cosmic rays and solar radiation. Astronauts and equipment must be shielded, and habitats may need to be partially buried or constructed, using materials that provide additional protection. Testing all of these systems is one of the most time-consuming aspects of preparing for lunar missions. Conditions on the Moon are difficult to replicate perfectly on Earth. Vacuum chambers, thermal testing facilities, and simulated lunar soils can approximate some aspects of the environment, but real conditions are always more complex. Engineers must therefore design with a margin of safety, accounting for uncertainties and ensuring that systems can tolerate unexpected variations. This cautious approach contributes to longer development timelines, but increases the likelihood that equipment will perform as intended. Another important consideration is integration. Each system, power, life support, communication, mobility, and others must work together seamlessly. A problem in one area can affect others, so engineers spend considerable time ensuring compatibility and reliability across the entire mission architecture. All of this work reflects a shift in how lunar exploration is viewed. The goal is no longer simply to visit the Moon, plant instruments, and return home. The vision now includes sustained presence, scientific research, and preparation for even more distant journeys. Achieving these goals requires equipment that is more capable, more durable, and more adaptable than anything used before. This increased ambition is part of what makes building for the Moon again such a formidable challenge. It is not a matter of repeating the past, but of preparing for a future that is broader in scope and longer in duration. Yet despite these challenges, progress continues. Engineers are developing new landers, new habitats, and new systems designed specifically for the lunar environment. Each test, each prototype, and each mission adds to the growing body of knowledge needed to support human activity on the Moon. It is tempting to imagine that once a technology has been invented, it can simply be built again whenever needed. After all, If engineers once designed a spacesuit that worked on the moon, or a lander that touched down safely on its surface, why not just reopen the blueprints and start assembling the same machines? Yet in practice, rebuilding these systems is rarely so straightforward. Materials change, manufacturing methods evolve, safety requirements become stricter, and the goals of missions themselves grow more ambitious. As a result, many of the tools needed for returning to the moon must be reinvented, even when their basic purpose remains the same. Spacesuits offer a particularly clear example of this process. To an outside observer, a spacesuit might appear to be little more than a protective garment, something like a very advanced diving suit. In reality, it is closer to a miniature spacecraft, a self-contained life support system that must keep its wearer alive in an environment that offers no air, no warmth, and no protection from radiation or micrometeoroids. During the Apollo missions, the suits worn by astronauts were marvels of engineering for their time. They provided oxygen, removed carbon dioxide, regulated temperature, and allowed enough mobility for astronauts to walk, bend, and work on the lunar surface. The suits functioned well, but they also had limitations that became apparent during longer excursions. Movement was physically demanding. The joints resisted motion, making simple tasks tiring. Dust clung stubbornly to the fabric, and repeated exposure caused wear. Designing modern spacesuits involves addressing these challenges while also meeting new requirements. Future missions may involve longer stays on the moon, more extensive exploration, and tasks that require greater flexibility and endurance. Engineers must therefore create suits that are more durable, easier to move in, and better able to resist the abrasive effects of lunar dust. One approach involves rethinking the structure of the suit itself. Instead of relying solely on pressurized fabric, some designs incorporate rigid or semi-rigid components that allow joints to move more naturally. Bearings and improved materials reduce the effort required to bend arms and legs. Advanced fabrics and coatings help prevent dust from adhering to surfaces. Life support systems have also advanced. Modern electronics allow for more precise monitoring of temperature, oxygen levels, and other critical factors. Batteries are more efficient, and cooling systems can be designed to operate for longer periods. These improvements enhance both safety and comfort, but they also introduce additional complexity, requiring careful integration and testing. Testing a spacesuit is itself a demanding process. Engineers must simulate the vacuum of space, the temperature extremes of the lunar environment, and the physical stresses of movement. Astronauts train in underwater facilities or specialized chambers to practice working in suits, providing feedback that helps refine the design. Each adjustment must be evaluated to ensure that it does not introduce new problems. Landers present another area where old ideas must be revisited and adapted. The lunar modules of the Apollo era were designed for specific missions, carrying 2 astronauts for relatively short stays. They were optimized for a particular set of conditions, landing sites, and operational timelines. Modern lunar landers are being developed with different objectives in mind. Some are designed to carry larger crews or heavier cargo. Others are intended to support missions to regions of the moon that were not visited before, including areas near the poles where lighting conditions and terrain differ significantly from the equatorial regions explored during Apollo. Landing in these areas requires new technologies. Precision navigation systems must guide spacecraft to safe touchdown points, avoiding hazards such as boulders, slopes, and shadowed craters. Sensors and cameras provide real-time data, allowing onboard computers to adjust the descent path as needed. Propulsion systems too are being re-examined. Advances in engine design and fuel efficiency offer opportunities to improve performance, but each new system must be tested extensively to ensure reliability. The engines used for lunar landings must be capable of throttling, adjusting their thrust smoothly to control the descent, a requirement that adds to their complexity. Another consideration is reusability. Some modern lander concepts are designed to be used multiple times, refueled either in lunar orbit or on the surface. This approach could reduce costs and support sustained exploration, but it also requires designing systems that can endure repeated cycles of operation and maintenance in a harsh environment. Habitats and support structures are also part of the reinvention process. During Apollo, astronauts lived and worked inside the lunar module for only a few days. Future missions may involve habitats that provide more space, better protection from radiation, and facilities for scientific research. Designing such habitats involves solving many interconnected problems. Structures must be lightweight enough to launch from Earth, but strong enough to withstand temperature changes and potential impacts from micrometeoroids. Airlocks must allow astronauts to enter and exit without allowing dust to contaminate the interior. Power systems must operate reliably through the long lunar night. Some proposed designs even involve using local materials, such as lunar soil, to build or shield structures. Techniques like 3D printing with regolith are being explored as ways to reduce the need to transport heavy materials from Earth. These ideas are promising, but they require extensive research and testing before they can be implemented safely. Communication systems also require careful design. Astronauts working on the Moon must remain in constant contact with mission control and with each other. The Moon's rotation and terrain can interfere with direct signals, especially in polar regions. Relay satellites and surface-based communication networks may be needed to ensure reliable coverage. Another area of reinvention involves tools and equipment used on the surface. Instruments must function in vacuum and extreme temperatures. Moving parts must operate without traditional lubricants, which can evaporate or degrade in space. Materials must be chosen to resist wear from dust and to maintain their properties over long periods. Even seemingly simple items, such as hand tools, must be designed with care. Astronauts wearing pressurized gloves have limited dexterity, so handles and controls must be large enough to manipulate easily. Fasteners and connectors must be designed to prevent accidental release or damage. Training for the use of this equipment is equally important. Astronauts must practice assembling structures, conducting experiments, and performing repairs while wearing suits and working in simulated lunar conditions. These exercises help identify potential problems and refine procedures before actual missions take place. One of the most interesting aspects of this process is how it blends old knowledge with new ideas. Engineers study the records of Apollo missions, learning from the successes and the difficulties encountered by earlier crews. They analyse photographs, reports, and even the wear patterns on returned equipment to understand how materials behaved on the Moon. At the same time, they apply modern technologies that were not available decades ago. Advanced sensors, improved computing power, and new manufacturing techniques open possibilities that earlier engineers could only imagine. The result is not a simple copy of past designs, but a new generation of systems inspired by them. This blending of past and present is part of what makes returning to the Moon both challenging and fascinating. It requires respecting the lessons of history while embracing the opportunities offered by modern science and engineering. When you look at the Moon in the night sky, it does not appear especially distant. It is large enough to show detail with the naked eye, bright enough to cast shadows, and familiar enough that it can feel almost like a neighbour. People have watched it all their lives, seeing it rise above rooftops or trees, following it through the phases of the month, and sometimes feeling as though it hangs just beyond the clouds, within reach if only one could travel high enough. This sense of nearness is a gentle illusion, created by perspective and by the way our minds interpret the sky. In reality, the Moon is much farther away than it appears, and that distance is one of the fundamental reasons why travelling there remains such a demanding undertaking. On average, the Moon orbits about 384,000 kilometres from Earth. That number can be difficult to visualise, so it can help to imagine it in more familiar terms. If you were able to drive a car continuously at highway speed without stopping, it would take many months to cover that distance. Even at the speed of a jet aircraft, the journey would last weeks. Spacecraft travel faster than either of these, of course, but even so, reaching the Moon requires several days of flight, distance in space is not only a matter of travel time, it also affects communication, navigation, and safety in ways that are less obvious, but equally important. Signals travelling at the speed of light take about 1.25 seconds to cross the gap between Earth and the Moon. That may not sound like much, but it means that every exchange between astronauts and mission control involves a brief but noticeable delay. Questions cannot be answered instantly. Commands cannot be corrected in real time. Crews must be prepared to make decisions independently, relying on training and procedures rather than immediate guidance. This delay becomes even more significant when considering emergencies. In low Earth orbit, astronauts are relatively close to home. If a serious problem occurs, there are possibilities for relatively rapid assistance or return. The International Space Station, for example, orbits only a few hundred kilometers above Earth, and spacecraft can reach it within hours. By contrast, astronauts travelling to the Moon are far beyond the reach of quick rescue. Once a spacecraft has left Earth orbit and begun its journey outward, it is largely on its own. Every system must function reliably, and crews must be capable of handling unexpected situations with the resources available on board. The journey itself is not simply a matter of pointing a rocket at the Moon and accelerating. Spacecraft must follow carefully calculated trajectories, balancing speed, fuel consumption, and the gravitational influences of Earth and the Moon. These trajectories are designed to ensure that the spacecraft arrives at the right place at the right time, with the correct orientation and velocity to enter lunar orbit or begin a descent to the surface. Achieving this precision requires careful planning and continuous monitoring. Small adjustments, known as course corrections, are often necessary during the flight. These maneuvers use onboard thrusters to fine-tune the spacecraft's path, ensuring that it remains on the intended trajectory. Navigation in deep space relies on a combination of methods. Instruments track the positions of stars, measuring angles and movements to determine orientation. Radio signals exchanged with Earth provide additional data, allowing ground teams to calculate the spacecraft's position and velocity with remarkable accuracy. Modern spacecraft may also use optical navigation, analysing images of the Moon or other celestial bodies to refine their estimates. All of these techniques must work together seamlessly, because even a small error can grow over the course of hundreds of thousands of kilometres. A trajectory that is off by a fraction of a degree at the beginning of the journey could result in missing the Moon entirely, or arriving at an unsafe speed or angle. Fuel requirements add another layer of complexity. Escaping Earth's gravity is only the first step. Slowing down to enter lunar orbit requires additional fuel, as does descending to the surface, and later launching back into orbit for the return journey. Every kilogram of fuel must be carried from Earth, and every kilogram adds to the weight that the rocket must lift at launch. This leads to one of the fundamental challenges of space travel, sometimes called the tyranny of the rocket equation. To carry more fuel, a rocket must be larger and more powerful. But making the rocket larger increases its weight, which in turn requires even more fuel. Engineers must carefully balance these factors, designing vehicles that can carry enough propellant to complete the mission without becoming impractically large or expensive. Distance also affects the reliability of equipment. Spacecraft travelling to the Moon must operate for days in the harsh environment of space before even reaching their destination. Systems must endure temperature extremes, radiation exposure, and the constant vibration and stress of launch and maneuvering. By the time astronauts arrive in lunar orbit, their spacecraft has already completed a demanding journey. Then there is the psychological dimension of distance. Being far from Earth is different from being in orbit nearby. The view from a spacecraft travelling to the Moon changes gradually as the planet recedes, shrinking from a vast horizon-filling presence to a small blue sphere suspended in darkness. For astronauts, this can be both awe-inspiring and humbling, a reminder of how isolated they are in the vastness of space. Communication delays, limited resources, and the knowledge that help is far away all contribute to a heightened sense of responsibility. Training and preparation are essential. not only for technical tasks but for maintaining focus and composure over the course of the mission. Another aspect of distance that is easy to overlook is the challenge of returning. Leaving the Moon requires launching from its surface, reaching orbit, and rendezvousing with another spacecraft. Then comes the journey back to Earth, which involves precise navigation and a carefully planned re-entry into the atmosphere. Re-entry itself is a delicate process. Spacecraft returning from the Moon travel much faster than those coming back from low Earth orbit, and the heat generated by friction with the atmosphere is correspondingly greater. Heat shields must be designed to withstand these extreme temperatures, and the angle of entry must be carefully controlled to ensure a safe descent. All of these factors mean that a lunar mission is not a short excursion, but a complex sequence of events extending over many days. Every phase must be planned in advance, every contingency considered, and every system tested thoroughly. There is also the matter of timing. Launch windows for lunar missions are determined by the positions of Earth and the Moon, as well as the desired landing site and trajectory. These windows may occur only at specific times, sometimes days or weeks apart. Missing a launch window can mean significant delays, requiring teams to wait for the next opportunity. The Moon's orbit itself is not perfectly circular, and its distance from Earth varies slightly over time. Engineers must account for these variations when planning missions, adjusting trajectories and fuel requirements accordingly. In recent years, interest has grown in exploring regions of the Moon that were not visited during the Apollo era, particularly near the poles. These areas offer intriguing possibilities, including the presence of water ice in permanently shadowed craters. However, reaching these regions can be more challenging than travelling to equatorial sites, requiring different trajectories and landing techniques. Establishing communication and navigation systems to support operations in these areas adds further complexity. Relay satellites may be needed to ensure continuous contact with Earth, especially for missions on the far side of the Moon, which never faces our planet directly. Distance also influences the logistics of supplying missions. Every piece of equipment, every tool, and every kilogram of food or water must be transported across that vast gap. For short missions, this is manageable, but for longer stays or permanent installations, the challenge becomes more significant. Engineers are exploring ways to reduce the amount of material that must be launched from Earth, using local resources on the Moon to produce water, oxygen, and even fuel. These technologies hold great promise, but they require careful development and testing before they can be relied upon. Despite all these challenges, the distance to the Moon is not insurmountable. Humanity has already crossed it many times, both with robotic spacecraft and with astronauts. What makes the journey demanding is not only the physical distance, but the combination of technical, logistical, and operational factors that must be managed simultaneously. Looking up at the Moon on a clear night, it is easy to forget these complexities. The Moon appears serene, unchanging, almost inviting in its quiet brightness. But reaching it requires navigating a path that stretches across space, guided by mathematics, sustained by engineering, and supported by the careful work of countless people. Arriving at the Moon is only part of the journey. The final phase, the descent and landing, is where the margin for error becomes smallest and the demands on both machines and people reach their peak. From orbit, the lunar surface appears calm and unchanging, a landscape of pale plains and darker patches, marked by craters that have remained untouched for millions or even billions of years. Yet that stillness hides a complicated reality. Landing on the Moon is not like landing on Earth, or even like landing on Mars. It requires a level of precision that has become, in some ways, even more demanding in the modern era. During the Apollo missions, landing sites were chosen with great care, but they were also selected with certain practical limitations in mind. Engineers favoured relatively flat regions near the lunar equator, areas where the lighting conditions were predictable, and the terrain, though not perfectly smooth, was considered manageable. Even then, the final approach often required astronauts to make manual adjustments, guiding the spacecraft away from hazards that became visible only in the last moments of descent. One of the most remarkable aspects of those early landings was how much depended on human judgment. Astronauts looked out of windows, studied the terrain, and sometimes took control of the lander to avoid boulders or slopes. That ability to adapt in real time was essential, but it also reflected the limits of technology at the time. Guidance computers were powerful for their era, yet far less capable than modern systems. Sensors were simpler, and digital mapping of the lunar surface was still in its infancy. Today, the expectations for landing have changed. Missions are no longer content simply to reach a broad, safe region. Scientists and engineers often want to land in very specific locations, sometimes only a few kilometers wide, because those places hold particular scientific interest or potential resources. Regions near the lunar poles, for example, are especially attractive because of the possibility of water ice in permanently shadowed craters. These areas may hold clues about the history of the solar system and could also provide materials for future exploration. Reaching such locations requires far greater precision than landing in the wide plains visited during Apollo. The terrain near the poles can be rugged, with steep slopes, deep shadows, and uneven surfaces that are difficult to interpret from orbit. Sunlight falls at low angles, creating long shadows that obscure details and make it harder for cameras and sensors to identify safe landing zones. Modern landers must therefore rely on advanced navigation systems capable of analysing the surface in real time. Cameras compare images taken during descent with detailed maps stored in onboard computers, allowing the spacecraft to determine its position with increasing accuracy as it approaches the ground. Laser altimeters measure distance to the surface, while radar systems assess speed and altitude. All of this information must be processed rapidly, guiding the engines and thrusters to adjust the descent path. The complexity of these systems introduces new challenges. Software must be reliable under every conceivable condition. Sensors must function correctly despite dust, glare, and temperature extremes. Engineers must test these systems thoroughly, often in simulated environments that attempt to replicate lunar conditions as closely as possible. Testing, however, can never perfectly reproduce the real environment. Gravity on Earth is stronger, and vacuum chambers, though impressive, cannot replicate every aspect of the lunar surface. As a result, engineers must design with a margin of safety, anticipating uncertainties and ensuring that landers can tolerate variations in terrain and conditions. Another factor that complicates modern landings is the growing emphasis on protecting both equipment and future exploration sites. The plume of a rocket engine during descent can scatter dust and small rocks over a wide area. During the Apollo missions, this was a concern but not a limiting factor, because landings were relatively infrequent and spread across different regions. In the future, if multiple missions use the same areas, or if infrastructure is established on the surface, managing the effects of landing becomes more important. Engineers are studying how engine exhaust interacts with lunar soil, exploring ways to minimize erosion and reduce the risk of damage to nearby equipment or habitats. Precision landing also affects mission planning in subtle ways. The closer a spacecraft must land to a specific target, the narrower the acceptable range of trajectories becomes. This means that launch windows and flight paths must be calculated with even greater care. Small variations in timing or velocity that might have been acceptable in earlier missions can now require adjustments or delays. There is also the challenge of coordinating landings with other elements of a mission. A lander may need to rendezvous with equipment already on the surface, or to deliver supplies to a specific location where astronauts will be working. Achieving this level of coordination requires careful navigation and communication, as well as reliable mapping of the lunar terrain. Mapping itself has improved dramatically since the 1960s. Orbiters equipped with high-resolution cameras and laser altimeters have produced detailed maps of the Moon's surface, revealing features as small as a few meters across. These maps provide invaluable data for planning landing sites, but they also highlight how complex the terrain can be. Areas that appear smooth from a distance may be dotted with small craters, rocks, and ridges that pose risks to landing spacecraft. Engineers must therefore balance competing priorities when selecting landing sites. Scientific interest, resource potential, safety, and accessibility all play a role. Sometimes the most scientifically valuable locations are also the most challenging to reach, requiring new technologies and careful preparation. The descent itself remains one of the most delicate phases of any mission. A spacecraft must reduce its orbital speed, descend toward the surface, and then slow to a gentle touchdown, all while maintaining stability and avoiding hazards. The engines must respond smoothly to commands, adjusting thrust precisely. Fuel consumption must be monitored carefully, because carrying extra fuel adds weight, but running out too soon is not an option. In modern missions, many of these processes are automated, guided by sophisticated software. Automation can improve precision and reduce the workload on astronauts, but it also means that the software must be thoroughly tested and validated. Engineers must consider how the system will respond not only under normal conditions, but also in the presence of unexpected sensor readings or minor malfunctions. Redundancy is often built into critical systems, allowing backups to take over if a component fails. This improves reliability but also adds complexity, requiring additional testing and integration. Weather is not a factor on the Moon in the way it is on Earth, but lighting conditions play a significant role. Shadows can be extremely dark, and temperatures in shadowed areas can be much lower than in sunlight. Landing sites must be chosen with attention to how sunlight will fall at different times, ensuring that solar panels can generate power and that equipment can operate within acceptable temperature ranges. Another subtle challenge involves the human element. Even with advanced automation, astronauts must be prepared to intervene if necessary. Training for this possibility involves extensive simulation, allowing crews to practice responding to a wide range of scenarios. Simulators can recreate the visual cues, instrument readings, and time pressures of a real descent, helping astronauts develop the confidence and judgment needed to act effectively. At the same time, modern missions often aim to reduce reliance on manual control, because automation can achieve levels of precision that are difficult for humans to match, especially in environments where visual cues may be limited or misleading. All of these factors combine to make precision landing a demanding task, one that requires the integration of navigation, propulsion, software, and human expertise. It is not merely a matter of reaching the Moon, but of arriving at exactly the right place, under exactly the right conditions, with systems that function flawlessly. The difficulty of this task is reflected in the experience of robotic missions as well. Several recent attempts to land on the Moon by various countries and organizations have encountered problems during descent, highlighting how challenging this phase remains even with modern technology. Each of these missions provides valuable lessons, contributing to a growing body of knowledge that will improve future landings. What is striking is that precision, once a secondary concern compared to simply reaching the Moon, has become central to modern exploration. As goals become more ambitious, as missions aim to stay longer and explore more challenging regions, the ability to land accurately and safely becomes increasingly important. Long after the excitement of launch and landing fades, the Moon reveals a different kind of challenge, one that does not arrive suddenly, but lingers quietly, hour after hour, day after day. Surviving on the lunar surface is not only about reaching it safely or touching down with precision. It is about enduring an environment that is, in many ways, more hostile than it first appears. From a distance, the Moon seems calm and unchanging. There is no weather, no storms sweeping across plains, no winds carrying sand through the air. Yet this stillness hides dangers that are subtle, persistent, and often invisible. Radiation, dust, and the relentless extremes of temperature combine to create conditions that demand careful preparation and constant vigilance. Radiation is perhaps the most serious of these hazards, though it is not something that can be seen or felt directly. On Earth, life is protected by two natural shields. The atmosphere absorbs much of the radiation arriving from space, and the planet's magnetic field deflects charged particles streaming from the sun and beyond. Together, these protections reduce radiation exposure to levels that are generally safe for humans. The Moon has neither of these shields. Its surface is exposed directly to the radiation of space, including energetic particles from the sun and cosmic rays that originate far beyond our solar system. For astronauts spending only a few days on the surface, as during the Apollo missions, this exposure was limited, though still carefully monitored. But for longer missions, lasting weeks or months, radiation becomes a much greater concern. Protecting astronauts from radiation requires thoughtful design. Spacecraft and habitats must include shielding, using materials that can absorb or deflect some of the incoming particles. Even so, shielding cannot block everything, especially the most energetic cosmic rays. Engineers must therefore balance weight and protection, because every additional layer of shielding adds mass that must be launched from Earth. Some proposed solutions involve using the Moon itself as part of the shield. Habitats could be covered with layers of lunar soil, known as regolith, which would provide natural protection against radiation. This approach is promising, but it requires equipment capable of moving and placing large amounts of material, as well as structures designed to support that weight. Solar storms present another challenge. Occasionally, the sun releases bursts of energetic particles that can dramatically increase radiation levels in space. Astronauts on the Moon would need a safe place to shelter during such events, areas within their habitat designed with extra shielding where exposure could be minimized until the storm passes. Monitoring radiation is therefore an essential part of any long-duration mission. Instruments measure the levels continuously, allowing crews to track their exposure and respond to changes. Planning activities around these risks becomes part of daily life, another quiet rhythm in the routine of living beyond Earth. If radiation is an invisible hazard, lunar dust is very much the opposite. It is everywhere, clinging to surfaces, drifting in small clouds when disturbed, and settling into every crevice. At first glance, it resembles fine grey powder, but under a microscope, each grain reveals sharp, jagged edges formed by billions of years of impacts that shattered rock without the smoothing effects of wind or water. During the Apollo missions, astronauts quickly learned how persistent this dust could be. It coated their suits, covered equipment, and followed them into the lunar module despite efforts to brush it away. Once inside, it floated in the cabin, carried by movements of air, settling on surfaces and even causing irritation in the eyes and throat. For short missions, this was an inconvenience, but for longer stays, dust becomes a more serious concern. Its abrasive nature can wear down seals and joints, reducing the reliability of machinery. It can interfere with optical instruments, reducing the effectiveness of cameras and sensors. It can also pose health risks if inhaled over long periods, as the fine particles may irritate or damage lung tissue. Managing lunar dust requires a combination of strategies. Airlocks must be designed to minimize the amount of dust carried inside. Suits may be stored outside habitats, attached to entry ports, so that astronauts can enter and exit without bringing the dust with them. Materials and coatings are being developed that resist the adhesion of dust, making it easier to remove. Even with these precautions, dust will remain a constant presence, a reminder that the lunar environment is not easily tamed. Temperature is another quiet but powerful force on the Moon. Without an atmosphere to distribute heat, temperatures vary dramatically between day and night. In sunlight, surfaces can become intensely hot, while in shadow, they can plunge to extreme cold. The lunar day itself lasts about 2 Earth weeks, followed by an equally long night. These long cycles create challenges for both equipment and humans. Electronics must operate within narrow temperature ranges, requiring insulation and active thermal control systems. Batteries must retain their capacity despite the cold. mechanical components must function without becoming brittle or seizing. For astronauts, maintaining a comfortable and safe environment inside habitats is essential. Heating and cooling systems must work reliably, adjusting to changing conditions and conserving energy whenever possible. Managing power becomes especially critical during the long lunar night, when solar panels cannot generate electricity and stored energy must sustain life support systems and equipment. The absence of atmosphere also means that micrometeoroids, tiny fragments of rock travelling at high speeds, can strike the surface without burning up as they would in Earth's skies. Most of these particles are very small, but their speed gives them significant energy. Spacecraft and habitats must be designed with protective layers capable of absorbing or deflecting such impacts. These impacts are usually too small to notice individually, but over time they contribute to the slow wear of exposed surfaces. Windows, solar panels, and instruments must be designed to withstand this steady, invisible bombardment. There is also the psychological dimension of living in such an environment. The Moon is a place of profound isolation. The horizon is close, the landscape largely unchanging, and the sky always black, even during the day. Earth appears as a distant sphere, beautiful but unreachable without a journey of several days. For astronauts accustomed to the presence of wind, weather, and the sounds of life, the silence of the Moon can feel striking. Inside habitats, systems hum and air circulates, but outside there is only stillness. Maintaining mental well-being in such conditions requires careful planning, including opportunities for communication with family, structured routines, and environments designed to be as comfortable as possible. Time itself feels different on the Moon. The long days and nights, the absence of familiar cycles of sunrise and sunset, and the need to follow mission schedules rather than natural rhythms all contribute to a sense that ordinary patterns have been left behind. Yet humans are adaptable. The history of exploration on Earth shows that people can learn to live in deserts, polar regions, and other extreme environments. The Moon presents new challenges, but the principles of preparation, teamwork, and resilience remain the same. Engineers and scientists are working steadily to address these quiet dangers. New materials are being developed to improve radiation shielding and resist dust. Habitat designs are being refined to provide better protection and comfort. Instruments are being tested in simulated lunar conditions, and robotic missions are gathering data that will help guide future crews. One of the most promising approaches involves using local resources to enhance survival. Lunar soil could be used not only for shielding, but also as raw material for construction, creating barriers that protect against radiation and micrometeoroids. Water ice, if extracted successfully, could support life support systems and reduce the need for supplies from Earth. These innovations reflect a broader shift in how lunar exploration is envisioned. The goal is no longer simply to visit and depart, but to remain, to learn how to live and work in an environment that is both beautiful and demanding. Despite all these challenges, the Moon continues to draw us. There is something compelling about its quiet presence, about the idea of standing on another world and looking back at the Earth rising above the horizon. The difficulties of radiation, dust, and temperature are real, but they are not insurmountable. They are problems to be understood, managed, and gradually overcome through careful design and persistent effort. Spending a few days on the Moon and living there for weeks or months may sound like variations of the same challenge, but in reality they are profoundly different undertakings. A short visit is, in many ways, like a carefully planned expedition. Every tool packed in advance, every hour scheduled, every system designed to function just long enough to complete the mission and return home. Staying, on the other hand, requires something closer to building a small, self-sustaining outpost in one of the most inhospitable environments imaginable. During the Apollo missions, astronauts remained on the lunar surface for relatively brief periods. The longest stays lasted only a few days, and the missions were designed with that time frame in mind. Supplies were carried from Earth, life support systems were sized for short durations, and equipment was built to function reliably for the limited time required. Once the objectives were completed, the astronauts departed, leaving the surface quiet once again. Extending that presence changes nearly everything. The first and most obvious difference is the need for continuous life support over much longer periods. Air must be replenished or recycled. Water must be conserved, purified, and reused. Waste must be managed safely and efficiently. Systems that function well for a few days must now operate reliably for weeks or months without failure. On Earth, such systems are often supported by extensive infrastructure and frequent maintenance. On the Moon, every component must be designed to function with minimal intervention, and spare parts must either be carried from Earth or produced locally. This requirement influences the design of everything from pumps and filters to electronic circuits and structural components. Food presents another challenge. For short missions, it is practical to bring pre-packaged meals from Earth. For longer stays, the volume and mass of food become significant considerations. Researchers are exploring methods of growing plants in controlled environments, using hydroponics or other techniques to produce fresh food, while also helping recycle air and water. These systems are promising, but they require careful management of light, temperature, and nutrients, all of which consume energy and resources. Energy itself becomes a central concern. A short mission can rely on stored power or solar panels sized for limited needs. A long-term presence requires a stable and abundant energy supply capable of supporting life support systems, communication equipment, scientific instruments, and possibly manufacturing processes. Solar power is an attractive option, especially in regions near the lunar poles where sunlight may be available for longer periods. But even there, energy storage and distribution remain complex tasks. Habitats must also be designed differently for long-term living. A small cabin suitable for a few days may feel cramped and uncomfortable over weeks or months. Living spaces must provide room to move, areas for work and rest, and environments that support both physical and psychological well-being. Lighting, noise levels, and even the colours of interior surfaces can influence how people feel over extended periods. Protection from radiation and micrometeoroids becomes more important as exposure time increases. Shielding that is adequate for a short stay may not be sufficient for longer missions. Some habitat designs incorporate thick walls, layers of lunar soil, or underground structures to provide additional protection. Maintenance is another factor that grows in importance over time. Machines and systems inevitably wear down. Filters clog, seals degrade, and electronic components can fail. On Earth, replacement parts and technical assistance are often readily available. On the Moon, crews must be prepared to perform repairs themselves, sometimes improvising solutions with limited resources. This need for self-reliance influences the design of equipment. Components must be modular, allowing damaged parts to be replaced without dismantling entire systems. Tools must be versatile and easy to use while wearing pressurized gloves. Diagnostic systems must help identify problems quickly, so that repairs can be made before small issues become serious. Transportation also becomes more complex when staying on the Moon. Short visits may involve only a few excursions near the landing site. Long-term exploration requires vehicles capable of travelling greater distances, carrying heavier loads, and operating reliably over extended periods. These vehicles must be maintained, fueled, and protected from dust and temperature extremes. Communication is another area where the demands increase. Maintaining a continuous link with Earth is essential for coordination, scientific collaboration, and the well-being of the crew. Establishing communication networks, possibly including satellites in lunar orbit, becomes part of the infrastructure required for sustained presence. Logistics, the movement of supplies and equipment, grows into a major undertaking. Regular missions may be needed to deliver food, spare parts, scientific instruments, and other necessities. Each of these missions requires launch vehicles, planning, and coordination. Reducing dependence on Earth by using local resources becomes increasingly important, but developing the technologies to extract and process those resources is itself a significant challenge. The human element is perhaps the most subtle and complex aspect of staying on the moon. Living in isolation, far from family and friends, in a confined environment with a small group of colleagues requires resilience and careful psychological preparation. Schedules must balance work and rest. Opportunities for recreation and communication must be provided. Even small comforts such as personal items or the ability to look at images of Earth can make a meaningful difference. Time perception can also change in such environments. The long lunar day and night cycle does not align with the natural rhythms of the human body, so artificial lighting and structured schedules are used to maintain regular sleep patterns. Maintaining a sense of normalcy becomes part of the daily routine, even in a place that is anything but ordinary. Medical care presents another layer of complexity. Minor injuries or illnesses that would be easily treated on Earth can become serious when far from hospitals and specialized equipment. Crews must be trained in medical procedures, and habitats must include supplies and tools for diagnosing and treating a range of conditions. Emergency planning becomes more demanding as well. In a short mission, the option of returning to Earth relatively quickly may be available. During a long-term stay, evacuation might take days or weeks to arrange, and immediate rescue may not be possible. Systems must therefore be designed with redundancy and resilience, ensuring that critical functions can continue even if some components fail. Environmental control within habitats is another constant concern. Air composition, humidity, temperature, and pressure must be maintained within safe limits. Sensors monitor these parameters continuously, and automated systems adjust conditions as needed. Over long periods, even small imbalances can have significant effects, so careful monitoring and maintenance are essential. Scientific work, which is often a primary motivation for staying on the moon, also requires infrastructure. Laboratories, instruments, and storage facilities must be provided, along with power and communication links to transmit data back to Earth. Experiments may run for months or years, requiring stable conditions and reliable support systems. One of the most intriguing possibilities associated with long-term lunar presence is the use of local materials to build and sustain infrastructure. Regolith could be used to produce building materials, shielding, or even components for manufacturing. Water ice, if accessible in sufficient quantities, could support life support systems and be split into hydrogen and oxygen for fuel. Developing these capabilities would mark a significant step towards self-sufficiency, reducing the need to transport every resource from Earth. But achieving this goal requires new technologies, extensive testing, and a gradual build-up of equipment and experience. All of these factors illustrate why staying on the moon is so much harder than visiting. A short mission is like a carefully planned journey, with a clear beginning and end. A sustained presence is more like establishing a small remote settlement, where every system must function continuously and reliably, and where the margin for error is small, yet the potential rewards are equally significant. A permanent or semi-permanent presence on the moon could support scientific research, provide a testing ground for technologies needed for missions to Mars, and deepen our understanding of how humans can live and work beyond Earth. In the decades since the last footprints were left on the moon, something has changed in the way space exploration is imagined. During the early years of the space age, missions beyond Earth orbit were often framed as competitions, visible demonstrations of national capability played out on a global stage. The urgency of that era drove remarkable achievements, but it also shaped the structure of the programs themselves. Today, the picture is more complex. Cooperation and competition now exist side by side, sometimes reinforcing each other, sometimes creating new challenges, but always influencing the pace and direction of the journey back to the moon. One of the most noticeable differences between the Apollo era and the present is the number of participants. In the 1960s, only a few nations possessed the technological and industrial capacity to attempt human spaceflight, and fewer still could consider travelling to the moon. Now, many countries operate satellites, launch vehicles and scientific missions. Space agencies across Europe, Asia and the Americas contribute to research and exploration, and private companies have become important partners in developing new technologies. This broader participation has opened the door to cooperation on a scale that would have been difficult to imagine in earlier decades. The International Space Station stands as one of the clearest examples of what can be achieved when multiple nations work together over long periods. Built and operated by a partnership of countries, it has hosted astronauts and experiments from around the world, demonstrating that collaboration can sustain complex projects in orbit for many years. The lessons learned from such partnerships are now influencing plans for returning to the moon. Instead of a single nation undertaking every aspect of a mission, different organisations may contribute landers, habitats, communication systems, or scientific instruments. This approach allows costs and expertise to be shared, making ambitious goals more achievable. At the same time, cooperation introduces new layers of complexity. Agreements must be negotiated, responsibilities defined, and technical standards harmonised. Spacecraft built in different countries must be able to connect and communicate reliably. Schedules must be coordinated, sometimes across organisations with different priorities and timelines. These processes require patience and diplomacy, as well as engineering skill. Decisions that might once have been made within a single agency now involve discussions among multiple partners. While this can slow progress in some respects, it also creates opportunities for broader participation and shared achievement. Alongside cooperation, a quieter form of competition has also re-emerged. Several nations have announced plans to send astronauts to the moon, establish research stations, or explore regions that were not visited during earlier missions. This renewed interest reflects both scientific curiosity and a recognition that the moon may play an important role in future exploration and resource utilization. Competition, when it remains constructive, can be a powerful motivator. It encourages innovation, accelerates development, and inspires public interest. The challenge is to balance this competitive energy with the practical benefits of collaboration, ensuring that efforts complement rather than duplicate each other. Private industry has added another dimension to this evolving landscape. Companies are developing launch vehicles, landers, and other technologies that were once the exclusive domain of government programs. Some of these companies operate as contractors, providing services to space agencies, while others pursue independent missions or partnerships. The involvement of private firms has introduced new business models and new approaches to problem solving. Rapid prototyping, iterative testing, and commercial investment have accelerated certain aspects of development. At the same time, integrating commercial systems into larger exploration programs requires careful coordination, particularly when human safety is involved. This blending of public and private efforts is reshaping how missions are planned and executed. Governments may define long-term objectives, such as establishing a sustained presence on the moon, while companies design and operate specific components of the infrastructure needed to achieve those goals. International cooperation also extends to scientific research. Lunar missions carry instruments designed by teams from multiple countries, each contributing to a shared understanding of the moon's history and environment. Data collected by orbiters and landers are often made available to researchers worldwide, fostering a sense of global participation in the exploration of space. Another important aspect of cooperation is the development of common standards and protocols. Docking mechanisms, communication systems, and safety procedures must be compatible if spacecraft from different organizations are to work together effectively. Establishing these standards requires negotiation and agreement, but it also creates a foundation for future missions that can build on shared infrastructure. There are also discussions about the legal and ethical frameworks that will guide activities on the moon. Questions about resource utilization, environmental protection, and the preservation of historic landing sites are being considered by international organizations and space agencies. These conversations are part of a broader effort to ensure that exploration proceeds responsibly and sustainably. Despite the emphasis on cooperation, the idea of a new space race is sometimes mentioned. This phrase reflects a recognition that nations are eager to achieve milestones, to demonstrate leadership, and to inspire their citizens. However, the nature of this competition differs from that of the past. It is less about a single dramatic victory and more about sustained capability, about building infrastructure and conducting research over many years. In this sense, the modern era of lunar exploration resembles a marathon more than a sprint. Success is measured not only by who arrives first, but by who can maintain a presence, conduct meaningful science, and contribute to the broader goals of exploration. The growing diversity of participants also means that knowledge and experience are being shared more widely. Engineers and scientists collaborate across borders, exchanging ideas and techniques. Students in universities around the world study space science and engineering, preparing to contribute to future missions. This global network of expertise strengthens the overall effort, even as individual nations pursue their own objectives. Communication technology plays an important role in supporting this cooperation. High-speed data links, video conferencing, and shared digital platforms allow teams separated by thousands of kilometers to work together effectively. Designs can be reviewed, simulations analyzed, and decisions made without the need for everyone to be in the same place. At the same time, cultural differences and varying organizational practices can present challenges. Approaches to problem-solving, management, and risk assessment may differ among partners, requiring careful coordination and mutual understanding. Building trust and effective working relationships becomes as important as solving technical problems. Public engagement is another area where cooperation and competition intersect. Space missions capture the imagination of people around the world, and agencies often share images, videos, and educational materials to inspire interest in science and technology. Collaborative missions provide opportunities for students and educators in many countries to participate in experiments or outreach activities. As plans for returning to the Moon continue to develop, it becomes clear that this new era of exploration is shaped by a complex interplay of factors. Cooperation enables projects that would be difficult for any single nation to undertake alone. Competition encourages innovation and maintains a sense of urgency. Private industry introduces new capabilities and perspectives. All of these elements contribute to the long road back to the Moon, a journey that is as much about building relationships and institutions as it is about building rockets and spacecraft. In recent years, the long and gradual effort to return humans to the Moon has begun to take on a clearer shape, guided by a new generation of spacecraft, new partnerships, and a broader vision of what exploration beyond Earth might become. This effort is often associated with a name drawn from ancient mythology, a name chosen to suggest continuity with the past while also pointing toward something new. The Artemis program represents not only a plan to land astronauts on the Moon again, but a plan to remain there, to build infrastructure, and to prepare for journeys that may one day extend far beyond the familiar orbit of our nearest celestial neighbour. To understand why this program is so different from the efforts of the past, it helps to consider the goals that shape it. The Apollo missions were driven by a clear and urgent objective: land humans on the Moon and return them safely to Earth. That objective was achieved with remarkable speed, but once it was accomplished, there was no equally urgent reason to continue at the same pace. Artemis, by contrast, is built around a longer horizon. The aim is not only to reach the Moon again, but to establish a sustainable presence, to learn how to live and work there, and to use those lessons as preparation for future missions to Mars and beyond. This shift in purpose changes the way spacecraft are designed and missions are planned. Instead of focusing on a single landing, the program envisions a sequence of missions, each building on the last. New vehicles are being developed to carry astronauts farther than any human spacecraft has travelled in decades. Systems are being created to support longer stays, more complex operations, and greater cooperation among different nations and organizations. One of the central elements of this effort is a new spacecraft designed to carry crews beyond Earth orbit. Unlike the vehicles used during the Apollo era, which were optimized for relatively short missions, this spacecraft is intended to support longer journeys and to integrate with a broader architecture of exploration. It must operate reliably in deep space, protect its crew from radiation, and provide the flexibility needed for a variety of mission profiles. Developing such a spacecraft is a complex undertaking. Engineers must balance many competing requirements: safety, weight, performance, and cost. Materials must be tested under extreme conditions. Systems must be designed with redundancy, ensuring that failures in one component do not endanger the entire mission. Software must be verified with extraordinary care, because modern spacecraft rely heavily on digital control systems. Testing plays a crucial role in this process. Before astronauts ever board a new vehicle, it must demonstrate its capabilities through uncrewed flights, carrying instruments that monitor every aspect of performance. Data from these missions are analysed in detail, guiding adjustments and improvements. Only after engineers are confident in the reliability of the systems do they proceed to crewed missions. Another important component of the new approach to lunar exploration is the concept of an orbital platform around the Moon, sometimes described as a small station that can serve as a staging point for missions to the surface. Such a platform would provide a place where spacecraft can dock, transfer supplies, and prepare for landings. It could also support scientific experiments and act as a relay for communications. Building and maintaining such an outpost in lunar orbit requires careful coordination and international cooperation. Modules may be contributed by different countries, each designed to integrate with the others. Launch schedules must be coordinated, and assembly procedures must be planned in detail. The result, if successful, will be a piece of infrastructure that extends human presence beyond Earth in a way that has not been achieved before. Landing systems are also being reimagined. New lunar landers are being designed to carry larger crews and heavier equipment than those used in the past. Some concepts involve reusable landers that can travel between the surface and orbit multiple times, reducing the need to build a new vehicle for each mission. Achieving this capability requires advances in propulsion, fuel storage, and maintenance procedures, as well as reliable methods for refueling in space or on the lunar surface. The involvement of commercial companies has become a defining feature of these efforts. Governments are working with private firms to develop launch vehicles, landers, and other systems, creating partnerships that combine public funding with private innovation. This approach introduces new dynamics, encouraging competition and rapid development, while also requiring careful oversight to ensure safety and reliability. Commercial participation also brings the possibility of more frequent missions and a wider range of applications. Companies may develop technologies that support not only government exploration programs, but also scientific research, communications, and other activities. This diversification could help sustain lunar exploration over the long term, making it less dependent on a single source of funding. International partners play an equally important role. Space agencies from multiple countries are contributing expertise, equipment, and scientific instruments. Agreements are being established to define how resources will be shared, how responsibilities will be divided, and how data will be distributed. These partnerships reflect a recognition that the challenges of exploring and living on the Moon are too great for any single nation to address alone. Training astronauts for these missions involves preparing them for conditions that differ in subtle ways from those of earlier programs. Longer missions require greater endurance and adaptability. Crews must be able to operate complex equipment, conduct scientific research, and respond to unexpected situations with limited support from Earth. Simulation facilities and training exercises are designed to replicate as many aspects of the lunar environment as possible, allowing astronauts to develop the skills and confidence they will need. Scientific objectives also play a central role in shaping the future of lunar exploration. The Moon preserves a record of the early solar system, its surface bearing the marks of impacts and geological processes that have been erased on Earth by weather and tectonic activity. Studying lunar rocks and soil can provide insights into the history of the Earth-Moon system and the broader evolution of planetary bodies. Regions near the lunar poles are of particular interest because they may contain deposits of water ice in permanently shadowed craters. If these resources can be accessed and used, they could support life support systems and provide raw materials for fuel production. Developing the technologies needed to extract and process these materials is an important step toward making long-term exploration more sustainable. Another aspect of the Artemis program involves testing technologies that will be needed for future missions to Mars. Living and working on the Moon offers an opportunity to gain experience in operating habitats, managing life support systems, and conducting surface operations in a reduced gravity environment. These lessons will be invaluable when planning journeys to destinations that are far more distant and challenging. Public interest in space exploration has also evolved. Advances in communication technology allow people around the world to follow missions in real time, watching launches, listening to astronauts, and viewing images transmitted from spacecraft. Educational programs and outreach efforts aim to inspire new generations of scientists, engineers, and explorers, ensuring that the knowledge and enthusiasm needed for future missions continue to grow. Despite all these advances, the path forward is not without obstacles. Developing new spacecraft and infrastructure requires significant investment and sustained political support. Technical challenges must be overcome, and schedules may shift as testing reveals issues that must be addressed. Progress in space exploration is rarely smooth or predictable, but each step forward adds to the body of knowledge and experience that makes the next step possible. One of the most significant differences between the current era and the time of Apollo is the emphasis on sustainability. The goal is not simply to plant a flag and return home, but to establish systems that can operate over many years, supporting ongoing research and exploration. This requires careful planning, reliable infrastructure, and a commitment to long-term investment. The idea of sustainability also influences how missions are designed. Reusable spacecraft, modular habitats, and the use of local resources are all part of a strategy aimed at reducing costs and increasing flexibility. These approaches require new technologies and new ways of thinking about exploration, but they also offer the potential to make human presence beyond Earth more practical and enduring. As these efforts continue, the Moon is gradually shifting in our collective imagination. It is no longer seen only as a distant object or a place visited briefly in the past. It is becoming a destination once again, a place where humans may live and work, conduct experiments, and prepare for journeys that will carry them even farther into the solar system. The work underway today represents the early stages of that transformation. Engineers design and test new systems, astronauts train for missions that will take them farther from Earth than any crew has travelled in generations. Scientists plan experiments that will deepen our understanding of the Moon and the history of our planetary neighbourhood. All of this progress is part of a larger story, one that connects the first tentative steps of the space age with the possibilities of the future. The road back to the Moon is long and complex, shaped by technology, politics, economics, and the quiet determination of people who believe that exploration is worth the effort. At this point in the journey, it helps to pause for a moment and consider everything that has quietly unfolded along the way. Returning to the Moon is often described as if it were a single task, something as simple in principle as building a rocket and flying it to a familiar destination. Yet when you look more closely, it becomes clear that the path back is not a straight line at all. It is more like a long, winding road, shaped by time, memory, changing priorities, and the steady accumulation of knowledge. The first journeys to the Moon now belong to history, yet they are not distant in the way ancient events are distant. We still have the recordings, the photographs, the rock samples preserved in laboratories, and the footprints resting undisturbed in the fine grey dust. In a sense, the moon still carries physical traces of those brief visits, quiet reminders that human beings once crossed that vast distance and stood there, looking back at Earth. And yet, despite that achievement, decades passed without another human return. That fact alone tells us something important about the nature of exploration. Reaching a new place once is an extraordinary accomplishment, but maintaining the ability to return again and again is often far more difficult. It requires continuity, commitment, and a willingness to sustain efforts over generations. Time has a way of reshaping everything. Technologies evolve, skills fade and are relearned, facilities are built, dismantled, and rebuilt in new forms. The world itself changes, and with it the reasons we pursue certain goals. The journey back to the moon has been shaped by all of these forces, sometimes moving forward quickly, sometimes slowing almost to a standstill but never truly stopping. One of the most interesting aspects of this long road is how much has been learned along the way, not only about rockets and spacecraft, but about the broader systems that make exploration possible. We have learned that complex knowledge cannot simply be stored in documents and retrieved unchanged decades later. It must be practiced, shared, and passed from one generation to the next. We have learned that infrastructure, once allowed to fade, takes time and patience to rebuild. And we have learned that the environment of space, so silent and beautiful from a distance, demands constant respect and careful preparation. There is also a deeper lesson, one that becomes clearer the more you think about it. Exploration is not only about reaching new places, it is about the process of learning, adapting, and growing as a species. Each challenge overcome adds to our understanding, not only of the universe but of ourselves, of what we can accomplish when curiosity and determination are combined with careful planning and steady effort. The moon, in this sense, has become more than a destination. It is a testing ground, a place where new technologies can be developed, where scientists can study the history of the solar system, and where astronauts can gain experience that may one day carry them even farther, perhaps to Mars, perhaps beyond. Looking back, it is easy to see the Apollo era as a moment of extraordinary speed and focus, a time when the goal was clear and the resources were concentrated. Looking at the present, the pace may seem slower, the path less direct, but this difference reflects a change in the nature of the journey itself. The aim is no longer simply to arrive and depart. It is to remain, to build, to learn how to live and work in environments far from Earth. That shift in perspective changes everything. Systems must last longer. Missions must be planned with sustainability in mind. International partnerships must be formed and maintained. Technologies must be tested not only for performance, but for durability and reliability over time. All of this takes patience. And patience, though less dramatic than a rocket launch, is one of the most important qualities in any long-term endeavour. If you think about it, the moon itself offers a quiet example of patience. It has circled the Earth for billions of years, unchanged in its slow, steady motion. It does not hurry, it does not compete, it simply continues, orbit after orbit, reflecting sunlight into the night sky. Human exploration moves on a different timescale, measured in decades rather than millennia, but the principle is similar. Progress often comes gradually, through small steps that accumulate over time. A new engine tested here, a navigation system refined there, a partnership formed, a mission planned, a launch completed. Each step may seem modest on its own, yet together they form the path forward. There is also something reassuring about the way knowledge builds across generations. The engineers and scientists working on lunar missions today grew up hearing the stories of Apollo, watching old footage, reading accounts of the first landings. Many of them were inspired by those events, and now they contribute their own ideas and skills to the next phase of exploration. In this way, the journey to the moon is not only a physical journey, but a human one. carried forward by curiosity and imagination as much as by rockets and machines. It is worth remembering too that exploration has always been part of human history. Long before spacecraft, people crossed oceans in fragile ships, navigated deserts and mountains, and ventured into unknown lands guided only by stars and determination. Each generation faced its own uncertainties, its own risks, and its own reasons for continuing. Space exploration is, in many ways, a continuation of that tradition, shaped by new technologies but driven by the same fundamental impulse to understand what lies beyond the horizon. And yet, unlike the explorers of the past, astronauts travelling to the moon carry with them a perspective that is uniquely modern. From the surface of another world, Earth appears small, a blue and white sphere suspended in darkness, without visible borders or divisions. That view has influenced many who have seen it, reminding them of how interconnected life on our planet truly is. Perhaps that perspective is one of the most valuable things gained from journeys beyond Earth, a quiet reminder that exploration is not only about reaching outward, but also about seeing home more clearly. As plans for future missions continue to develop, there will undoubtedly be challenges ahead. Technical problems will arise, schedules will shift, and unexpected obstacles will appear, as they always do in complex endeavours. But the steady progress already made suggests that the road back to the moon, though long, is very much open. One day, astronauts will again step onto the lunar surface, not as the first visitors but as the next in a continuing story. They will bring new tools, new experiments, and new questions. They may remain longer, travel farther, and begin to build the foundations of a lasting presence. And somewhere in that quiet landscape not far from where they work, the footprints left decades earlier will still be there, unchanged, a silent connection between past and present. If you imagine that scene for a moment, it becomes clear that exploration is never truly finished. Each achievement becomes the starting point for the next, each discovery opening the door to new questions. The moon is not the end of the journey, only one step along a path that stretches outward into the vastness of space. For now, though, it is enough to rest with that thought, to picture the Earth and the moon together, turning slowly in the darkness, bound by gravity and by the quiet persistence of human curiosity. And as the night deepens, wherever you happen to be listening, you might find it comforting to remember that above you, beyond the clouds and the shifting air, that familiar pale world is still there, moving in its silent orbit, waiting patiently as it always has, while humanity, step by careful step, finds its way back.